He has focused particularly in SMT solvers and applications to them. And today, I'm very curious to see his talk, he'll talk about how to devise new ways of combining reasoners, going beyond the traditional ways employed by the automated reasoning community to have these systems cooperate. So thanks, Stefan, and you have the floor.
Thank you. Does this microphone work? Or should I have, hello, is this better? Yeah. Okay, I'll use this. Thank you, Henya, for the introduction. Thank you so much for the organizers of the symposium. Thank you, Edgar, and all your team for the organization. Thank you to the program committee for inviting me. It's an honor to be here. I came here, I followed Monday and Tuesday, and those were already 2 great days. And if you attended Monday and Tuesday, you may already have heard of SMT solvers as part of this big landscape of formal methods. So I'm going to start slowly introducing SMT solvers and what they're all about, and then go further into what we're doing at SRI International in that particular area of formal methods. So what is SMT solving? SMT stands for SAT modular theories, and it's one particular approach to automated reasoning. And by automated reasoning, I mean you have a formula and you want to prove it, or you want to disprove it with a counterexample. There are several ways to tackle this problem, and SMT solving is one of them. So the way that it works is that if you want to automatically prove a formula F, in other words, you want to show that F is valid, then you're going to negate F and see if you can find a solution or an example of the negation of F. That would be a counterexample to F being valid. So SMT solving is really taking this refutational approach in which you're searching for a counterexample to the theorem that you want to prove. Okay. So you can see this as a constraint solving problem. Not F is a bunch of constraints, and you're trying to satisfy not F. And if you do manage to do that, you've got your counterexample, and you can say, no, F is not a theorem. Otherwise, you say, well, I can't find, there aren't any solutions to not F. And in that case, you can conclude that not F is unsatisfiable, meaning that your original formula F is a theorem. Okay, so that it's in that sense that SMT solving is really an automated reasoning approach. So SMT solving searches for solutions to constraints, right? So that's what it is. What is it good for? What is it used for? Well, again, if you attended Monday and Tuesday, you've heard SMT solvers being used mostly as a back end to many pipelines in formal methods. And I'm just mentioning here a few approaches in formal methods that you may have heard of, which at the end of the day rely on SMT solvers to solve these problems. Deductive verification, automated code analysis, model checking, proof assistance if you want to prove theorems, complicated maths, interactively in a proof assistant, then you want some automation to help you do that, and SMT solvers provide one form of automation for that. Which brings me to the third question, how is it done? How does SMT solving broaches the problem of solving those constraints? It's a very pragmatic field, right? You just look at the kind of problems that you want to solve, the kind of algorithms that exist in the world for solving some of these problems, and you try to use the best algorithm for the problem at hand, okay? And often problems are complicated and are hybrid, and they are multifaceted, and it's the job of SMT solver developers to actually organize those different algorithms to make them collaborate in subtle ways in order to solve these problems. So you take reasoners, algorithms, that are designed for specific constraint solving tasks. So imagine that, for instance, you have a Boolean problem that you want to solve, a SAT problem, where in that case, you know that you have SAT solvers that are going to do that job really well. So use them. If you have a linear arithmetic problem to solve, then you know that there are algorithms like the simplex algorithm that is going to be really good at finding solutions to these linear constraints. So use that. And so for each kind of problem, you've got procedures, algorithms that you can use. And the field of SMT solving is about making them collaborate in organizing this search. Okay? So the main idea here is that if you have a complex solving task, let's call it J, you want to split it into smaller tasks. You want to decompose your problem into smaller problems. And each of those smaller problems, you can give it to a particular algorithm, a particular procedure that's going to treat that well. Okay. So yeah, you decompose a problem into tasks, each of which fits into the scope of applicability of one of your dedicated reasoners. Oops. All right. So here's a list of examples of theories, mathematical theories, kinds of constraint solving problems that we know good algorithms for, or at least some algorithms for. Okay. Boolean logic, SAT solving, CDCL, right? Equality with uninterpreted symbols, congruence closure, egraph are going to help you there. Different kinds of arithmetic, linear, nonlinear, integer, real arithmetic. For all of those, we have methods. The theory of bit vectors, the theory of arrays, tuplers, we mentioned tuplers 2 days ago, I think. Option types, data types, sequences, strings, finite set. Now field arithmetic is one of the latest additions. Okay. So lots of different mathematical theories for which we know how to solve. We know some method for trying to solve them. I mean, some of these problems are really hard, but at least we know some algorithms for doing for treating them. All right, so here's the plan for my talk. I'm going to describe a brief journey from something called Nelson Open, which is a way of combining some of these procedures, to something called Seeger, counterexample guided abstraction refinement, and I'm going to explain what that is. Then we're going to describe how at SRI International we are using approximations of formulas to make the problems that we want to treat simpler. It's usually good to start with approximations and then refine those approximations. So we have techniques to produce under approximations and over approximations that are used in algorithms. I'm going to go into that a little bit. Then I'm going to talk about a variant of Seeger called region Seeger. It's a name I came up with yesterday. I'm not sure it's the best name. If anybody has another suggestion, they're welcome. And some of the experiments that we conducted using that variant of Seeger in arithmetic. And then I'm going to briefly come back to the kind of theory of how you combine procedures together, especially in a way that those procedures actually share a common data structure in order to build a solution of your constraints. So it's a way of collaborating that's very kind of hands-on, and everybody works on the same data structure and tries to build the solution together. And there are several questions with this. One of them is, what do you require? What are the specs? What are the requirements on those theory reasoners that you need for that to work? And so there's a completeness requirement, and then there's a termination requirement. At some point in time, you want to have an answer to your problem. So the question of termination is important in many aspects. In some aspects, you know that you're not going to get it, and it's still useful to have semi-decision procedures. But yeah, termination is still an important aspect. All right. So coming back to this idea that the main idea of SMT solving is you've got a complex problem, you're going to decompose it into subtasks. okay, and treat them separately. So a typical situation in which you may want to do that, splitting a task into smaller tasks, is when you're required, when the problem is to solve a satisfiability query for a quantified free formula. And that's got to be decided in a union of two theories, T1 and T2. And you so happen to have a decision procedure for T1 and a decision procedure for T2. The question is, how can you leverage them in order to answer a satisfiability question involving both T1 and T2? Okay. So the high-level solution to that problem is that you're going to what we call purify your constraints, your input formula F, into a T1 part and a T2 part. That's not too complicated to do. The only requirement that you have here is that the original formula F is satisfiable in T1 and T2, if and only if the conjunction of T1 and T2, sorry, the conjunction of F1 and F2, which are the two parts of your formula that you produce, is satisfiable in T1, T2. Okay? So you decompose the problem syntactically. And then what you do is that you're going to ask the question, well, is there a model M1 of F1, so a T1 model of F1? And separately, you are going to ask the question, is there a T2 model of F2? Okay. And if the answer is yes, yes, then you hope that somehow you can glue the models together in order to have a combined solution of the original formula. Okay. So basically, if you manage to find a solution for half of your formula, for F1, a solution for the other half of your formula, F2, and it so happened that those two solutions, they may overlap, but on the parts where they overlap, they actually agree, then you can glue those two solutions together as a solution to the original problem. Okay? So let's forget a little bit about the agreement requirement. If you didn't have that, life would be simpler, right? You just run your decision procedure, your T1 decision procedure on F1. You get an answer, yes or no. You run your T2 decision procedure, P2 on F2. You get an answer, yes or no. And if both say yes, you say yes. If one of them says no, you say no. That would be a simple word if you didn't have to somehow make those two solutions agree on their overlap. So here's a little picture explaining this. You start. Do you have a pointer here? Yes. Which one is it? Yeah. You start with your original problem F. You purify it into two parts, F1 and F2. And there's a little bit of orchestration to call the two procedures, P1 and P2, and F1 and F2. And then you answer SAT or unsat. Okay. Now, of course, there's this question of disagreement. Okay, life is not that simple. So a typical requirement that we have in order to glue those two, to be able to glue those together, is to ask for the two theories T1 and T2 to be disjoint. In other words, there are a lot of syntax. What can they share? They can share sorts, and they can share equality, because equality is a symbol that everybody knows. Okay, so they share sorts of equalities, but nothing else. That's disjoint. Now, if they don't even share sorts, then the problem is really trivial, and the agreement requirement is trivially true. So it only becomes interesting once they start sharing some sorts. Now, when your theories are disjoint, the agreement requirement, like the when can we say that the overlap of the two solutions, when can we say that the two solutions agree on the overlap? Well, they should agree on equalities, and they should agree on the way to interpret sorts. Okay, that's quite natural. Let's start with the cardinality question. You've got a sort S that's shared between the two theories. Well, if one solution says that sort S has cardinality 3, and the other solution says sort S has cardinality 10, then you have a problem. They don't agree on the cardinality of the sort. So that's the first thing that you need to ensure, that the two sorts are interpreted as sets having the same cardinality. And the other thing that they need to agree on is what's equal to what, Okay, if they share the equality symbol, they need to agree on what's equal to 1. So in the two formulas F1 and F2, these two formulas, they don't share much, but they share some variables. There are some variables in common on both sides. So if one model says that, let's take two of these variables, x and y. Let's say that the first solution says, well, in my solution, x is equal to y. And then in the other solution for F2, that solution says, well, in my solution, x is different from y, then you have a problem. They don't agree. Okay? So you have to make sure that they agree. So you have to make sure that they agree on the shared variables, meaning that you should find a partitioning of your shared variables, okay, that they both agree on. Partitioning meaning, well, what are the equivalence class of variables that are equal to each other in the model. In other words, if one model says that x equals y, then the other model should say that x equals y, and vice versa. So these are the two things that you need to make sure of in order for the two models to agree and for you to recompose a combined model. All right, so regarding the agreement on equalities, things are not too bad because you only need the two models to agree on the equality between the shared variables, and your two formulas, F1 and F2, are finite objects. They have finitely many variables, okay? So there are only finitely many cases that you need to look at. Okay, there are only finitely many partitionings of those shared variables that you need to look at. So one trivial thing that you can do, I'm not saying it's the best thing to do, but that's a trivial thing to do, is simply to range over all possible partitionings of those shared variables. There are finitely many of them, that's fine. You can have a for loop. And in each case, you ask procedure P1, can you satisfy F1 and this particular partitioning? That kind of partitioning is called an arrangement for some reason in the field. Okay. And you ask P2, well, can you satisfy P2 with the same arrangement, with the same partitioning? If both of them say yes, you've won. If one of them says no, that doesn't work, then you move on to the next partitioning. And you've got a for loop, and you've got finitely many iterations, and you can conclude. Okay? Of course, there are many optimizations on this. You can, instead of ranging over all possible arrangements, there are actually exponentially many with respect to the number of shared variables. You can start giving the description of the partitioning incrementally to P1 and P2. Like maybe P1 is going to disagree on the fact that x equals y. There's no need to, you can rule out all of the partitionings where x equals y. You can also make P1 and P2 exchange what they think, which equalities they think should hold and which equalities they think shouldn't hold. That's one way of optimizing the scheme. Okay. But it's not too complicated. Let's move on to the other issue, making those two models agree, which is the cardinalities of shared sorts. So a typical thing that you require, that was in the Nelson-Open theorem in already 1979, which is to require that the two theories, T1 and T2, are what we call stably infinite. That's a bit of a weird expression. It just means that you can assume without loss of generality that the models have the cardinality of n. Okay? Meaning that if you had a model of cardinality 4, then you would also have a model of cardinality n. So you can assume without loss of generality that your models have cardinality n, and therefore T1 and T2 agree on this cardinality n. Okay. Now when I say a model has cardinality n, I'm being a bit ambiguous here because there may be several sorts involved, and some of the sorts may may have this property without loss of generality. You can assume that the cardinality of the sort is n, and then for other sorts, it's not the case. So you can refine this notion of stably infinite on a per sort basis, and that helps you a little bit. You can also kind of relax the stably infinite condition of Nelson-Open by saying, well, between T1 and T2, maybe T1 has a really strong opinion of what the cardinality of sort S should be. Maybe it thinks it has to be a cardinality 16. And maybe theory T2 doesn't care. So whatever, whatever you say. That's typically the case, like bit vectors, the theory of bit vectors. There's a sort like, what's my example? BV4. The sorts of bit vectors of length 4, where there are exactly 16 of them. Like it's got cardinality 16. There are 16 bit vectors of. Is that correct? Actually, yeah, I think it's 16. I've done it. Yeah. Right. And the other theory, maybe that sort is shared, but they don't really know what this sort is, and they don't really care what the cardinality of this thing is. So you can have this kind of asymmetry between the two theories about how opinionated they are about the cardinality of sorts. So if you're in that situation, that's also good. You've got one theory determining the cardinality, and then the other theory is just aligning itself with it. Okay, so that's captured in the notion of strong politeness that came a bit later. And that can also be done on a personal basis. All right, but generally speaking, whether you are in the original setup of the Nelson-Open theorem or relaxations of it, what I call a Nelson-Open-like combination is one of those pictures in which you purify. You've got a little orchestrator. Maybe it's going to range over arrangements. Maybe it's going to do a bunch of things. But it's basically going to interact with your dedicated procedures by sending satisfiability queries. Like this is the main API. This is the main interface of those procedures. It's just solving satisfiability queries, and that's it. So the correctness of a Nelson-Open-like combination relies on a bunch of properties holding. Three properties holding. The first one is a relation between the procedure P1 and the theory T1. What's the spec of the procedure P1 with respect to T1? Well, usually here you expect P1 to be a decision procedure for the satisfiability in T1, meaning that it should be sound, complete, and terminating. Okay. Same thing, the other thing that your correctness relies on is a relation between P2 and T2. Again, P2 should be sound, complete, and terminating for theory T2. And then you've got another kind of requirement that you have about the theories T1 and T2 themselves. Maybe you need them to be stably infinite. Maybe you need them to be, you need one of them to be polite, etc. Okay? So the correctness of the scheme is based on these properties. So in this talk, I'm going to survey some work that we did, in which we are going to require more out of those procedures P1 and P2. Either we are going to require them, we are going to interact with them in a slightly richer API than just sending them satisfiability queries, or we are going to ask them to satisfy some slightly stronger requirement than just being a sound and complete and terminating procedure for the satisfiability in the respective theory. Okay. All right, so a good thing about this Nelson-Open or Nelson-Open-like combination is that the theory immediately gives you an implementation. You see the theorem, you say, okay, I can implement this. You've got two procedures, you can arrange over arrangements, etc. It's quite direct to go from the paper description to an actual implementation. However, in practice, SMT solvers go way beyond that. Okay, and in particular, they employ theory reasoners that do a lot more than just answering satisfiability queries. For instance, in case they find SAT, you may want them to produce a model, an actual concrete model that you can read. Okay, that's something that a lot of the pipelines in formal methods require. If they answer unsat, those theory reasoners, you may want them to produce what we call an unsat core. So if you've got a bunch of constraints that you need to satisfy and you conclude that they're not satisfiable, maybe you want to identify a subset of your constraints that is already unsatisfiable. Okay, that's what we call an unsat core. Maybe you want them to propagate some theory literals that are implied by the inputs in a proactive way. oh, you're asking me to satisfy this? Well, if that thing is satisfiable, then that thing and that thing and that thing had better be true as well. Okay. They may provide canonizers to normalize terms. So there's a slightly more complex combination scheme that Nelson opened that's called the Shostak theory combination scheme, in which you're requiring your theory reasoners to provide some canonizers to normalize terms. SMT solvers do a lot of pre-processing and in-processing, rewriting terms and formulas. So you may have theory-specific ways of doing that. So you may require your theory reasoners to offer you some rewrite rules, for instance, in order to do some pre-processing or some in-processing. Maybe your theories, when they do the job, they need to do some case analyses. And maybe you want to delegate the case analysis to the logic that handles disjunction, the Boolean logic, okay, and the Boolean solver. That's called splitting on demand. Maybe you want them to produce under approximations and over approximations of formulas, and we're going to see an example later. Okay, so in practice, SMT solvers are actually requiring or leveraging a lot more out of the theory reasoners than just answering satisfiability queries. So let's concentrate on the first item here. That in the case of SAT, you want the theory reasoner to actually produce a model. Well, as soon as you have that, you can kind of start revising this Nelson open combination scheme by actually putting that concrete model in the picture. So you've got your formula F, and you purify it into F1, F2, and you start by asking the satisfiability query to F1, to R1 on F1, and well, if that theory reasoner says unsat, then there's not even a point asking R2 to reason about F2, right? But if it says sat, and if it can produce a model, then you can pass on this model to the other reasoner, and the other reasoner can inspect it and look at which variables are equal to which, possibly even what the cardinalities of the sort are, depending on how do you describe your model M1. But you can pass on the model to the other theory, and the other theory can either agree with it, saying, okay, I can work with that, I can extend it into something that satisfies my own axioms, or reject it. And if it rejects it, then it has to teach something to the first theory, some kind of lemma, that's going to prompt the first theory to actually revise the model and produce another one. Okay. Okay. So an example of this is you can do this between the Boolean theory and another theory in some kind of combination that here I'm going to call CDCLT, even though, well, okay. Let's call this CDCLT. Let's say that your original formula, you abstract it into a Boolean form. You abstract away everything that's not Boolean. You just retain the Boolean structure of the formula. You're going to give this part to a SAT solver, to a Boolean reasoner. And the Boolean reasoner is going to offer a Boolean model, okay? And is going to pass on this Boolean model to the theory, and every Boolean variable in the Boolean abstraction here corresponds to an atom in the theory, right? So if the SAT solver is producing a model in which Boolean variable x should be true, Boolean variable y should be false, etc., then that translates into a bunch of theory literals having to hold together for the theory, and then you are going to ask the theory, well, is this conjunction of theory literals something that's satisfiable for you or not? Okay. So you've got a Boolean model to the theory, and the theory is either going to complete that Boolean model into a theory model M, or say, well, no, the truth values of those theory atoms, they can't hold together. That's inconsistent with my axioms. So it needs to teach the SAT solver, hey, here's a lemma that's going to prompt the SAT solver to produce another Boolean model. That's usually called a theory lemma. Okay. All right, so this theory lemma is a lemma that justifies why this particular conjunction of theory atoms is not satisfiable for T. Okay. And actually, if the formula T here is able to produce an unsat core, it's actually able to identify a particular part of the model that's already problematic. Okay, and that speeds things up. Okay, so in real life, CDCL of T is a little bit more subtle because you may not want to wait until you have a full Boolean model of your Boolean abstraction before you ask theory T, hey, is that good with you? You may want a tighter loop in which you ask the theory T about consistency, or about T consistency on the fly, especially because CDCL works in an incremental way. It's building a Boolean model by making decisions and propagations, so it's doing things incrementally. And you may want to ask the theory T if, you know, at several points of this incremental construction, is this good for you so far? Okay. And so this is an important aspect. You don't want to wait until you have a full Boolean model. Typically, you ask the theory if things are good so far just before you make a decision, a Boolean decision. All right, so if we come back to the question of cardinality of shared sorts here, well, it's very easy in that case because there's only one shared sort, it's the Boolean sort, and everybody knows that the Boolean sort has cardinality too. Okay, so all models will agree on that. So there's no issue here with cardinality. Now this kind of revision of the Nelson-Open scheme in which you pass on a model happens to be an instance of something called CIGR, counterexample guided abstraction refinement. And it's a scheme that's present in many aspects of formal methods, but it's present in SMT solvers quite a lot, and that's one of the instances. So why is it called a counterexample guided abstraction refinement? Well, you've got an abstraction here, and you can see the model produced by the first reasoner as a counterexample to the unsatisfiability of this abstraction. Okay? And that counterexample may be also a counterexample to the original formula. That's when T says, yeah, okay. But it can also be a spurious counterexample. And if it's a spurious counterexample, the theory lemma that is taught, that comes back from the theory reasoner and taught to CDCL, that theory lemma is going to refine the original abstraction into a better abstraction, making it closer to the semantics of the original formula. So you've got this abstraction, you've got a counterexample, and when it is spurious, then that allows you to refine your abstraction. Okay. So this is the picture for the CIGR loop in SMT in general. You've got a formula. You're going to abstract it into something that your base theory is going to understand, or your base reasoner is going to understand. Then it's going to produce, well, maybe it's going to say unsat, but if it says sat, it's going to produce a model which you can see as a counterexample to the insatisfiability of F1. And then R2 is either going to accept this or send a lemma that refines the abstraction. Okay. So that happens to be the way that we actually, the way that in YIKES, so YIKES is the SRI International's SMT solver, and it supports a bunch of theories, but maybe at some point a user wants a theory that YIKES doesn't support. Okay, that can happen. So what do you do in that case? One of the things that you can do is to add to YIKES some user-defined theories. And the software architecture that we propose in order to do that is precisely this CIGR thing. So if you've got a theory that's not supported by YIKES natively, then what the user can do is, well, produce a way to abstract what you really want to solve into something that YIKES can understand. Okay. That's the first piece that you need to provide. And the second piece that you need to provide is a kind of model validation component that's going to take as input a model produced by YIKES and either convert it or extend it into a model of the original formula for your user theory, or send a lemma back to Yikes explaining, well, the model that you just spat out is not good for my axioms. You need to revise it into something different. Okay, so it's a very simple interface. If you have a theory that doesn't exist in Yikes and you want to add it, you just have to implement that, and it works. Okay. The second good thing is that you can stack this scheme up. Okay, you can do that one time, you can do that 2 times, 3 times. You can stack theories on top of each other in a Seeger loop that's iterated. Okay, so you can have an original formula, it gets abstracted, it gets abstracted, it gets abstracted, and at every stage you have this little loop here. Okay, so either you come out with unsat from the base reasoner, or somehow the base reasoner has given a model that the second reasoner has been able to extend, that the third reasoner has been able to extend, that the last reasoner has been able to extend into a model of the original formula. So it's a nice scheme because you can stack it up really easily. All right. I'm going to give a second example beyond CDCLT and Nelson Open to some extent. So the third example, I guess, of a Seeger loop in SMT solving. It's the way that they handle quantifiers. A very typical way for SMT solvers to handle quantifiers is, so imagine that your original formula here has some quantifiers. At first, you're going to ignore them. Ignore all the constraints that are universally quantified, like that have 4 rows. So you have a ground, what we call a ground abstraction, or a quantifier-free abstraction of your original input, and you feed that to your base SMT solver that doesn't understand quantifiers. We call that the ground solver. And the ground solver is either going to say unsat, or it's going to produce a model. Now, once you have a model, you can look at this model, look at the universally quantified constraints that you've ignored so far, and try to see if the model satisfies those constraints as well. And in many cases, it won't. So what you'll do is that you have a quantifier instantiation component here that's going to try and find a universally quantified constraint, and a ground instantiation of it that's going to defeat the model that was produced by the ground solver. Saying, okay, ground solver, you gave me this model. Now, if I instantiate my universally quantified constraints in this way, then look, you've got something that your model violates, so you need to revise your model and propose another one. Okay. So the lemma that's fed back to the ground solver, in that case, is a ground instance of a universally quantified constraint. Okay. But this is exactly the same scheme as before. Okay. Now that brings me to a piece of work that we did over the past couple of years, and it was presented at CADE this summer, which is also a way of dealing with quantifiers for special kinds of theories. It's basically a refinement of what I had on the previous slide. You see that the picture gets a bit more complicated. So so QSMA is the name of the algorithm. It stands for Quantified Satisfiability Modulo Assignment and Theory. It's implemented in an extension of Yikes called YikesQS. And the point is to solve constraints with quantifiers. And with quantifiers in a particular theory, like arithmetic, let's say, or bit vectors, and the quantifiers can occur anywhere in the constraint that you have to satisfy. Maybe at the top, maybe deeply nested, and there could be an arbitrary number of nestings of quantifiers in that constraint. So the algorithm takes as input a formula F with quantifiers, but it also takes a second input, which is a model M that's already forcing a bunch of free variables to have particular values. Okay. So what you do is you've got the formula F, same thing, you ignore the universally quantified subformulas or subconstraints in order to get a ground constraint to solve. And you've got a ground solver. Same thing, the ground solver is going to produce a model, and now you're going to look at whether this model also satisfies the universally quantified constraint that you've ignored so far. So for simplicity here, well, we can kind of assume that there's only one of these universally quantified constraints. That's typically the case if the formula F here is in pre-next form. You only have one universally quantified constraint, but the implementation actually accepts more than one. But for simplicity, let's say that you have to satisfy this for all x, a of x. So what are you going to do? You've got a model that the ground solver has produced while completely ignoring this constraint. What you're going to do is that you're going to call QSMA recursively. Okay, it's a recursive algorithm, and you're going to call it on the negation of a of x. So M here doesn't know about the x variables, right? The x variables are bound here. Okay, so M is not assigning any values to the x variables. But by calling QSMA recursively on not a of x, you are technically asking the question, can you find values for the x variables such that not a holds? Meaning, and if you can, then it means that your model M ground is violating this universally quantified constraint. Okay? And if you can't, then it means that your M ground model does satisfy this universally quantified constraint. Okay? So you call yourself recursively on the negation of the body of the universally quantified constraint. Okay. Is there any question here? Is that you're trying to defeat the model by finding essentially what is a counterexample to this for all formula. Okay, so if the recursive call must take a model as extra input, then the top level call also gets a model as input because it's recursive. Okay, and at the very top you can start with the empty model. Okay, so what happens next? What happens next is, well, this recursive call, it may say yes or no, right? I can find values for the x variables or I can't. Now, depending on this, you're going to do one of two things. If it says yes, if it says SAT, essentially, I was able to find values for the x variables, then you know that your model M is not good. Okay, you need to revise it. But if the only thing that the ground solver learns is that the model M ground didn't work, then you just know that this particular model didn't work. Let's try another one. You're in danger of enumerating an infinite number of models, right? You need to learn something. You need to learn what was it about M ground that made you able to find values for the x variables. Okay, you want an explanation. You want a reason that explains what did you not like in M ground. Okay, because when I'm going to revise M ground, I need to revise it in a better way. Okay. So the recursive call here, when it says SAT, it has to accompany the SAT answer with this kind of description, with an explanation of what was it about M ground that allowed me to find values for the x variables. And this is expressed in the formula U. And it's U for under approximation. If you want to know why it's called an under approximation, it's an under approximation of the formula that exists in X such that not A of X that's satisfied by M ground. So it's something about M ground, it's satisfied by M ground, that explains why you were able to find values for the X variables. Okay, and the ground solver can leverage this in order to produce a better model. Now, dually, it's also interesting when the recursive call says, I wasn't able to find values for the x variables. Okay, when it says unsat, it's also very useful if that happens, if the recursive call can also explain what was it about M ground that made me unable to find values for the x variables. Okay, so when it says unsat, then it's going to so it's an over-approximation this of the formula that exists in X such that's not A of X. That's not satisfied by M ground. And if that's your outcome of the recursive call, then you know that M ground does satisfy the universally quantified constraint, and then you can exit. Okay. But a key part of this QSMA algorithm is really this ability to produce explanations. So that's one of the aspects in which we're really requiring the theory reasoner to do more than just answer satisfiability queries and answer SAT or unsat. Okay, you want them to explain their answer. Like you told me SAT, what was it about my input model that made you answer SAT? You told me you conclude unsat, what was it about your input model that allowed you to conclude unsat? And this is really important. Okay, so this is a little graphical explanation of these under and over approximations. Imagine that your ground model is assigning values to two variables, z1 and z2. In other words, your ground model is a point in that plane, M, like this blue dot here. Okay? And the recursive code is going to try and see if it can find an x, a value for x, that satisfies a particular relation, which in that case is not A. Okay? And this not A is here represented in this blue shape. Ooh, okay. So if the ground model happens to be in the shadow, in the projection of this blue shape, then you know that there exists an X satisfying not A, okay? And the explanation that the recursive code is going to produce is not exactly this gray shape. I mean, the gray shape would be the perfect explanation. It really captures exactly what does it mean for, for the existence of X. But usually this shape is pretty complicated. What you can do instead is to under-approximate it, saying, well, M allowed me to find a value for X, but look, here's a class of models that would all satisfy the same property that would allow me to find a value for X. Okay, so that's what you're producing, and that's what you're teaching to the caller. And the dual situation is when the ground model is here, meaning that you can't find a value for X satisfying not A. Okay, so M here is outside of the shadow. And same thing, you want an explanation of what was it about that point M that made me unable to find a value for X. And so you come up with a formula that describes this red ellipse, saying, look, as long as you're going to be outside of this ellipse, I'm not going to be able to find values for X. Okay, so that's the kind of explanation that you come up with. All right, so this QSMA algorithm turned out to be really efficient on some of the theories involved in the SMT competition. So I'm going to shamelessly here put the theory for which it has the best results. I mean, there are other theories for which it also works, for some very well, for some a bit less well. But this is really the best result. Look, for LRA, so that's linear rational arithmetic with quantifiers, YAX-QS, which implements QSMA, is this line here. It solves way more problems than any of the other solvers in a lot less time. This is the logarithmic scale of runtimes.
That's not 2002, right?
This is 2002, and the, oh, sorry. 2022. Okay. Yeah, apologies. Yeah, 2022. I could have put the picture for 2023 because we already know the results for the SMT competition in 2023. And it looks exactly the same, so I just didn't bother to change it. Nothing really moved. All right. So let me go to the pros and cons of this Seeger loop in SMT solving. So I've put here the same picture as before. Now, amongst the pros, there's no real requirement for theory disjointness, because if R1 describes its model to R2, then R2 can, even if they're not disjoint, R2 can look at what the model says on their overlap and say, yeah, I agree with that, or no, I disagree with that. Okay. But there are a couple of cons. Okay. First, you need a reasoner R2 that's able to read a model that's passed from another theory. That's not typical in a theory API. A bigger problem is termination. Like in the Nelson open scheme, it was very simple. If you've got maybe one loop that ranges over all arrangements, and for each iteration of the loop, you have one satisfiability query to R1, one satisfiability query to R2, and that's it. Okay, so you know that it terminates. When you have this Seeger loop, how many times are you going to iterate over models and lemmas that are learned? Okay, can we bound the number of iterations of that loop? Now, irrespective of termination, passing fully concrete models may be inefficient, and this, I'm going to show an example on the next slide. Okay, so we had an idea at SRI about, well, we had a frustration. Okay, the frustration was we have two solvers for arithmetic, one based on the simplex algorithm that handles linear arithmetic, and one based on what's called cylindrical algebraic decomposition that's able to also treat non-linear constraints. Okay. But the thing is that the simplex-based algorithm is really fast on linear constraints, and when you run this MCSAT algorithm, so the one that's based on cylindrical algebraic decomposition, so it handles non-linear constraints, but in particular, you can also run it on linear constraints. And when you do that, you realize that it's way slower than the simplex on linear constraints. Okay? So if you have a problem that's 100% linear, then just run the simplex-based algorithm. Okay, that's very, very clear. What if you have a problem that's 99% linear, and you've got one nonlinearity somewhere? You know, this is a frustrating situation because you know that you have at some point to use the MCSAT algorithm because the simplex is not going to understand that 1% of nonlinearity. But the question is, can you actually still somehow leverage this simplex-based algorithm in order to give you a boost instead of just relying on this MCSAT algorithm? Okay, so the answer is yes, make the two solvers collaborate. And the question is, well, can you use the Seeger loop for that? So imagine here, you've got the same situation as before. You've got the simplex algorithm running here on a linear abstraction of the original formula. It's going to produce some models that are all valid for the linear constraints, that all satisfy the linear constraints. And then you've got this MCSAT box that's going to look at this model and also to make those models satisfy the nonlinear constraints. Okay. Now, if you just do that, it's not going to work. It's going to be terribly inefficient. Okay, because the simplex is going to assign a value to all the variables. And what are the chances that those values happen to satisfy the nonlinear constraints? 0 or close to 0, right? So you would have to be really lucky. And say that you have a constraint like x squared equals 2. Okay, you know that your solution is square root of 2, right? Or minus square root of 2. Well, the simplex is never ever going to produce such a value. The simplex-based algorithm doesn't even know about algebraic numbers. It only knows about rational numbers. Okay. So if in this Seeger loop you only produce one model at a time, then you're going to iterate a lot and possibly infinitely many times. What we propose instead is to actually have the first solver propose not one model, but a class of models. Okay, with a guarantee that any point in that class is already a model that satisfies the linear part of the constraints. But by providing a class, then you're giving the other solver some freedom, right, to range over that class, and within that class, pick a solution that also satisfies the nonlinear constraints. Okay, so that's something that we explored in the DARPA IDAS project. It's a collaboration between SRI International and Apogee Research. It's a project that's looking at symmetries in programming and formal methods in general. And the connection with symmetries here is that from the point of view of satisfying the linear constraints, a lot of solutions may be equivalent or symmetric to each other, but they're not all equivalent for satisfying the nonlinear part. Okay, and here's the result this is really a preliminary experiment that we actually did after I sent my abstract to SBMF. So after I sent the abstract, I thought, hey, we could do that. So, you know, this is really preliminary results. Here's the runtimes on QFN array. So this time it's nonlinear constraints. And the baseline is just running MCSAT on this. Okay. And the second line here is this IDAS approach in which we are doing this Seeger loop, but communicating classes of models. Okay, and the result essentially is that, and it was very easy to implement. It's like 300 lines of code max. is that we solve 200 more benchmarks in this entity, but also in half the time. Okay. And something interesting is that there's a cutoff point here around 0.1 seconds. Like below 0.1 seconds, these are really easy problems. So MCSAT can actually deal with them fine. Like you don't need to run the simplex algorithm before or during. But after 0.1 seconds, when you get to harder problems, then it starts paying off, having runs of the simplex every now and then. And what the simplex does is actually bringing MCSAT's attention to particular areas of the search space. Like what the simplex is doing is really, hey, look at this area of the simplex. Everybody here already satisfies the linear constraints, so have a look at that. And if in that area there's no solution to the nonlinear constraints, fine, let's look for another area. But it's like the simplex is really implementing some kind of torchlight, okay, in the search space. It's telling MCSAT, hey, look there. No? Okay, look there, okay? It's really this kind of iteration. And it starts paying off after 0.1 seconds. So there's a question of how do you actually describe class of solutions? Like in what form do you actually communicate class of solutions to? And I want to skip that because it's not super interesting. But one thing that we find promising in this approach, so this is just a little experiment in arithmetic that we can refine and explore. There's a question of variable ordering that you can play with, etc. But maybe we can actually apply that to other theories. And one that I have in mind is the theory of bit vectors. Theory of bit vectors is really hard. And the reason is that it's multifaceted. It's actually lots of theories merged together. With bit vectors, you can represent arithmetic operations. You can have extraction and concatenation. You can have bitwise operation. So it's really a theory that's actually the superposition of different things. Okay. The only problem is that you can't approach the theory of bit vectors with some kind of Nelson open approach because those kind of mini bit vector theories are not disjoint. Okay, they all share the same values, like bit strings. But in this scheme, you saw in arithmetic here, the simplex and MCSAT, also they're not disjoint at all. Actually, one theory is included in the other. It's really the worst case of non-disjointness, right? But yet it's useful. It's a useful scheme for making several reasoners collaborate, even though they don't work on disjoint theories. So there are various approaches for dealing with bit vectors. There's bit blasting. I think we've heard about it on Monday and Tuesday. There's a technique called int blasting. Like if your bit vector constraints are all about bit vector arithmetic, then maybe you can map all of that into the theory of integer arithmetic with a modulo and sort of there. We have several fragments of the theory of bit vectors for which we have really good word-level reasoning techniques, local search, etc. So you could imagine try to make all those different reasoners collaborate together because each of them is good on a particular fragment of the bit vector theory, just like the simplex is good on a particular fragment of arithmetic, namely the linear one. Okay, so that's the next thing that we want to do. And I think I'm running out of time. So, all right, so I'm going to go to the conclusion. The things I want you to retain. So, computing and communicating models, classes of models, under approximations, over approximations is really useful for combining reasoners, okay? Beyond the standard API of a satisfiability procedure. Seeger is a simple and practical scheme that goes a pretty long way for extending a solver's capability. If your solver doesn't have this capability, try to see if you can extend it with a Seeger loop in order to support, I don't know, something new like tuples, or actually for tuples you don't even need this loop, but arrays with length, for instance. Okay. Region Seeger, which is the name I gave to this adaptation of the Seeger scheme in which instead of communicating one model at a time, you actually communicate a class or a region of models at each iteration, is even a better way, particularly for non-disjoint combinations, like in arithmetic. And we're currently exploring its application to bit vectors as a theory combination problem. Then there are 2 points which are the 2 points that I skipped, which are what are the requirements that you impose theoretically on the theory reasoners, like completeness, terminations, etc. We have some criteria for that that goes beyond Nelson Open criteria. And what's interesting is that recently we extended those requirements in the kind of meta theory of when is it that the combined scheme is sound and complete. We've extended that to non-disjoint combinations where theories can share predicates. And we applied that new way of combining non-disjoint theories to a particular theory, which is the theory of arrays extended with the notion of abstract length or notion of domain. So in SMT solving, the theory of arrays doesn't have a notion of domain, or like you can ask what's the value that's stored in the array at index blah, and there's no question of whether blah is out of bounds or anything. So the theory of arrays in SMT is pretty trivial there. But we've extended it with a notion of an array having a domain. Perhaps it's any integer between 0 and some length. Okay. Now, what's problematic with this is that if you do that, then your theory starts interfering, namely being non-disjoint with, say, the theory of arithmetic. Like now, if your arrays have bounds between 0 and 10, you need, whenever you read in the array or you write in the array, you have to make sure that the index where you read or write is between 0 and 10 or 0 and 9. Okay. So that interferes with the theory of arithmetic that has to reason about what does it mean to be smaller than. Okay. So that's an example in which if you want to add a notion of length or domain to your array, you actually need to be in a non-disjoint combination with some other theory like arithmetic. All right, and I'm going to stop here. Thanks. Sorry for the overtime.
Thanks, Stefan, for the talk. Do we have questions? Yes, please, let me get you the mic.
Thanks for the talk. It was really illuminating. I always use SMT as a black box, so it's nice to see a little bit how it works inside. I'm a bit curious about this region system that you shared with us. Can maybe it's a stupid question from an engineering perspective, but is a region something that has a natural mathematical definition that is obvious that this is how it is, or is there some room for optimization on how you define these regions? And can you share some examples of what these regions look like?
Yeah, so there are two aspects to this. There's the kind of pure mathematical aspect. It's really a class of models. So it's a particular area of the search space for which you know every point in that area is a solution to my problem. So mathematically, you just said like at this level of abstraction, there's it's pretty simple. What becomes tricky is how do you represent them? How do you encode them practically? How do you communicate them, and etc. So that's kind of one of the things I skipped. I don't have an ideal answer to this. We tried something which is what I call a dependent Cartesian product. Okay, so it's actually a very almost programmatic description of the region. In the sense that you're describing how to sample from this region, how to generate points within this region. And you say, well, take the first variable x1. If you want to be in the region, you need x1 to satisfy some bounds, being between 0 and 10, etc. Now pick a value for that. Now move on to the next variable x2. Now I'm going to give you some constraints about x2 and about the value that you picked for x1 in order for you to pick the value for x2. And for x3, now you've picked values for x1, x2, and I'm going to give you some constraints about the first three variables. So it's kind of a recipe about how do you construct a point in that region. So you may say, well, it's yet another satisfiability problem. You've got some constraints, you've got to solve them. But it's true, like these are constraints, but they are already in a solved form. Like if you think of, yeah.
No, that makes a lot of sense. But for example, here why such a thing? Like, is this more efficient than having like a bunch of constraints over the whole variable vector, just having Rk at the end? So is there an advantage of having this sort of chain system where you start with only one variable, then two variables?
Yeah, because in this recipe for constructing models, you know that you don't have to backtrack. If you follow the recipe, at no point will you pick a value for some variable, make a few more steps, then realize, damn, that's not good. I need to backtrack and pick another value. Okay, so that's what I mean by it's a problem that's already in a solved form, in that you don't need to backtrack in order to construct things in it. I mean, there's an example here, which is, imagine you have, this is the simplest most trivial example. X is smaller than 3, x3 is, sorry, x1 is smaller than x3, x3 is smaller or equal to x2, and then you put a class of solutions, actually in that case it's all the solutions, in this dependent Cartesian product form. For x1, what are your choices? Well, pick anything you want. I don't care about x1, pick anything you want. But for x2, you pick anything you want, but it has to be above x1. Because if it's not, then you may have a problem at the point when you pick x3, right? So for x2, pick anything that's bigger than the value you picked for x1. Then for x3, you need to be between x1 and x2. But it's almost like the original problem, except that you've inferred this thing in the middle, which helps you traverse your class without backtracking.
Any further questions? So I have a question. So you said that you were thinking of calling this approach region-based, well, region-seeker, right?
Yeah, I've played with Surgar, like counterexample region guided abstraction refinement, but it starts being a bit.
So yeah, so it's about the region part, because
Yeah.
in a sense, I mean, when you have CDCL that you're doing conflict-driven closed learning, you also are interested in ruling out a class of solutions rather than just a single point, because if you, in a sense, because if you just got like exactly the trail rather than a subset of the trail that you determine a different way, then you are excluding more possible models than just that one that would fail. And we also generally call that Seeger. So like, don't you think that it's kind of a silly question, but don't you think that that name already captures already the idea that you are discussing?
Well, what you're saying here, if I understand correctly, is that what you learn from a failed model, what you learn here is going to exclude that model and many others.
Yes.
And that's already in Seeger, and that's already granted. What we observed in a couple of applications of that is that there may be many parts in that model that are actually not very relevant for the first solver, but somehow it had to decide a value, because when you ask for a model, you ask a value for everything. And we observed in a couple of examples that a lot of iterations were just due to the second reasoner rejecting things that the first reasoner didn't really care about. It simply had to produce a value. And there were a lot of useless iterations coming from that. So the idea of the region seeker is that the first reasoner is going to abstract away everything that it doesn't care about. Like, if in order to satisfy your constraints, you need x to be between 0 and 10, don't randomly guess a value that x equals 5. Because then the second reasoner may disagree with that and say, oh no, 5 doesn't work, I need to explain what's wrong with 5, etc. The idea is to avoid overcommitting to some of the values in the model, so that the second reasoner has the flexibility to decide what it's in better position to decide, instead of having to teach plenty of lemmas just to reject those wild guesses that the first reasoner did but didn't have to.
I see. Thanks. Further questions? Okay, so let's thank Stefan again, and
Thank
we're
you.
going to have a short break now.
Hi everyone, my name is Luis Sautier. Thank you, Vince, for the introduction. I'd like to thank also Professor Edjard, Raniel for the event, the staff and organization. I'm from Federal University of Technology on Paraná, and I'm gonna talk about how to automatically generate code for desk controllers model as automata, as finite state machines. First, I'll explain a little bit about controlling, and then about DES, which stands for Discrete Event Systems, how we control them. Then about our implementation called Desk Maker. A little case study of this implementation will be presented next, and then some discussions and perspectives. So first, on computer system engineering, we use formal methods for the development of automatic control systems solutions. So we have a lot of examples, but our main goal is to develop these control solutions for industrial practice. We have also other examples as precision medicine, agriculture, cyber physical systems, but formal methods can be used to create these called correct by construction control solutions. We can create the model that is used for controlling the system, especially for discrete event systems. But what's a discrete event systems? A discrete event systems, it has a set of states. Here you can see as S1 to S6. And these states in the system, they are changed via events. So we have some events here, E1, E2, E3. These events, they occur at certain points in time. So we have the changing from one state to another. Normally this change is instantly, but we don't have equations to model the systems like other types of systems. So we can use finite state machines, ordinary automata, to create the model of the system, to model how the behavior of the system is. How we do that? First, we define the alphabet. It is the set of events, the events that can happen within the system. The events can be of two kinds. The first kind is the controllable events, and the other kind, the uncontrollable events. I will talk about them a little bit next. Then we have the set of states, all the states that the system can reach, some initial state, and the set of marked states, and the transition system. Here we have a little automata representing these sets and definitions. So we have the supervisor control theory, which is the theory that says how we do that, how we can calculate the controller for certain DAS system, DAS example. How we do that? First, we have to create models from the plant, G, and each specification, E. Then we can combine those models, G and E, to obtain a certain finite state machine called K. And then we use a process called synthesis to calculate a finite state machine called S. This S is called the supervisor. So we use the supervisor for implementation. So this is the process we use to calculate these finite state machines for implementation of the controller. I brought you a little example. So imagine we have machine 1 and machine 2, and machine 1 takes some raw material and produces a certain piece in a process. The raw material entering machine 1 is called event A, and the produced piece is called event B. Machine 1 producing the piece is called event B. I can model this behavior by this finite state machine. So I have one state here, and by event A, the machine starts producing the piece, and after the piece is produced, event B reaches the initial state again. In the same way, I can model the machine 2, where I have this produced piece as input, and it performs some kind of cutting in the piece, and I have a star-shaped piece here. So the event of input for machine 2 is C, and the event of producing a star-shaped piece is D. I can also model the machine 2 as a two-state finite state machine. And I have a buffer here. How can I model this buffer? We call these specifications. So if I only use those two machines, I can have things I don't want, like C being able of happening before A or B. So I have to create a specification. Let's say this buffer has of 3 pieces. And then this automaton can model these 3 maximum capacity. So after 3 Bs, 3 pieces are put in the buffer. B is blocked, cannot happen, is disabled. This specification together with the 2 plant models can be used to calculate the K automata. So this automaton can be used for implementation. However, it has some problems, like here and here. Because some events are controllable, and what is a controllable event? Well, A and C is something that I have as input for my system. I gave A to the machine and C to the machine. So these 2 events I can control. But B and D, they cannot be controlled. Why? Because the machine has some kind of inner process, and I cannot know for sure when that process is completed. So we say that B and D are uncontrollable events. So after calculating K, which is just the synchronous composition of those 3 automata, I have to calculate S, eliminating states, blocking, or trying to control uncontrollable things. And this S automata can be used for implementation purpose. This is called the Supremo model. So this way we can model the plant and specifications and calculate the supervisor. After that, the supervisor is converted to code, and we can put that code in something like a microcontroller and connect to the actual plant in an industrial practice to control that industrial plant. However, we identify some gaps in the literature. The supervisor control theory is well supported by software, modeling software like Supremica. This kind of software provides intuitive modeling environment and model checking. However, it does not support code generation. We have some tools that support code generation, like this tool, this lab, and others. However, those tools do not support modeling, simulation, and synthesis, calculating the supervisor, model checking. So, and also those approaches, they do not include outputs for higher level data science languages like Python. So where is our contribution? So this paper introduces the Desk Maker tool, which is designed to generate C code for controllers that were modeled, synthesized, and checked in Supremica. The code can be directly transferred to compatible hardware and tested on computer prior to deployment. And also, we developed a Python version of this tool called Desk Python Maker. Here we can see the framework for the Desk Maker implementation. So first, we have as input the Supremica file. The Supremica file is structured as a XML format. It contains elements and attributes to represent events, the plants, and supervisors. And within each supervisor, XML elements represent events and transitions. We convert this Supremica file to C or Python file using templates. So the Python routine converts this Supremica file to the C project. And depending on the target platform, moving the files to a specific structure may be necessary. That depends on the user, but the conversion of the supervisor is automatic. Here we have the controller structure. Basically, it has two parts. The first part, the superior part, is the automatically generated code, where we have the supervisor or supervisors and the event handler. And the user has to define interfaces for uncontrollable events, normally inputs to the controller, and actions associated with controllable events, normally something to do, like turn on a machine or send an email, for example. We model the supervisor structure like this. So we have the supervisor, initial state, current state, last state, and alphabet, like I said before. All the events that are possible to happen, the state, transition, and the event type, if it's controllable or uncontrollable. Next, we have the event handler. It manages the events of the controller. Every event must be submitted to event handler through the trigger event function. So it's a routine, a function that executes something regarding that event. Let's say turn on a machine or maybe send an email. The event handler checks whether the event is enabled by supervisor. Sometimes the supervisor can disable some events, so that's checked at each event. And if it is enabled, it is executed. So we make the transition to the final state machine, call the function that is associated with that event, and manage the controllable events enabled in the plant. Here is our case study. So we have two moving conveyors. Moving the work pieces from one conveyor to another is our goal. When this start button is pressed, the conveyor 1 turns on, this one. And when sensor 1 detects an item, conveyor 1 is turned off. So we have sensor 1 right here. So the piece comes from here to here. And when the sensor grab, which is right here, detects the item, it activates the grab, moves up the z-axis of the arm, and moves the item to the other conveyor. When it reaches the destination, it turns off conveyor 2 and releases in this area. When we release, it turns on conveyor 2 and returns the arm. In parallel, as soon as the workpiece is grabbed at the z-axis moves up, it turns on the conveyor 1. So sensors 6 and 7 indicate whether the z and axis are moving or not. How we did that? So we modeled first the plants. Here we have the 5 sensors that have a defined state. Just go up and down really quickly. Here we have the model for the other 2 sensors, 6 and 7. And here we have the model for the actuators, the motors, from the axis Z and X and the conveyors. Also, S and F are controllable, only the controllable events. All sensors are uncontrollable. Here we have the specifications of how this should work. I just I'm gonna show them here, but I'm gonna present how the specifications work later. But basically they have to coordinate the start of conveyor 1 according to the start button, turn off conveyor 1 Every time an item arrives at sensor 1, and so on. So we did the modeling, the synthesis and implementation. We had 11 local supervisors that were converted, uploaded to DeskMaker. DeskMaker then converted the models to C code, and the C code was embedded on ESP32. On the user section routines, we had to write the routines to connecting to Wi-Fi network, to the Modbus TCP server, and functions for reading the inputs and controlling the outputs. The average real time to generate the files was around 300 milliseconds, and here we have the memory numbers, around 10,000 bytes in flash and run. Here we have the video. Could you please click the video there? Of the case study running under control. I think. So we have a piece here, and the grab just grabs the pieces and puts on the conveyor too. So we can see the system is working according to the models that I presented previously. DeskMaker is a tool for creating C code for controllers automatically that have been designed, synthesized, and verified in Supremica. A case study was conducted. The design of the project facilitates the implementation of hybrid control by allowing the user to control the execution of the control algorithms in the user area. The event handler, which is the bottom part, can interconnect the supervisor in the physical plant, so the user can change. The event handler acts as an interface between these two layers, allowing replacement of one of them or both without code refactoring of the supervisor. We have a Python implementation, that's Python Maker, that generate code in Python. The DeskMaker, as presented, is only designed to deal with ordinary automata, but in the future we can use other types of automata, like timed automata. Other concepts such as time automata will be explored next. And also we have to see a little bit about the implementation. We use linked lists, but maybe tables are better. We have to test that. Here are the acknowledgements. So thank you.
So thank you very much for this interesting talk. Do you have questions? Yes?
As an you calculate the product of them prior to generating the C code. After that, do you also calculate the minimal state machine equivalent to that, or do you just use the raw product?
We have to calculate one supervisor for each specification. So we take the plant models and we synchronize with each of the specifications. So we generate one supervisor for each specification, but there is no reduction after that.
Okay, thank you.
Other questions? I have one related to this. So you're saying that you create one specification or one supervisor for each of these specifications. How do they interact?
Okay, so we have in control theory, we have a property that the modular supervisors are not non-blocking. So one cannot say something that other one can say different things. So we had a blocking state. But basically they behave in synchronous composition. One event that's enabled in all of them can happen. If the event is not in their alphabet, it can also happen. But if the event is the alphabet but is blocked in all supervisors.
Thank you. Other questions? Okay, so let's thank the speaker. Thank you very much.
Thank you.
One of these properties is non-interference that ensures that low output of programs do not depend on high input during its execution. And an important feature of this property is that it can be enforced statically by the definition of an information flow type system. In those type systems, program variables are classified in different types according to the kind of information they store. For example, we will have private variables, confidential variables, etc. The problem with non-interference is that it results very restrictive for some applications that must allow intentional information behavior. For example, in a password checking program, it is possible to learn a small amount of information in each attempt. In a purchase payment program, to carry out the purchase, we need to verify that the amount of money in a wallet is enough to carry on the purchase. So, to make security language practical, mechanisms for declassifying or releasing information in a controlled way are needed. And a critical part of this mechanism is to ensure that the classification is used safely. The information flow policy, namely the limited release, was introduced by Sabelfeld and Meyers and guarantee that the intentional release of information cannot be used to infer more information than it should. And these properties can also be enforced statically by type system. And in this work, I will present an embedded domain-specific language in Haskell to ensure for enforcing this security property to type programs. This is the approach we follow. In language with powerful type system, it is possible to encode data invariants that are property about programs at type levels. And then that invariants become part of the ordinary code and can be statically checked at compile time. And that is the purpose of what we want to do. That is something very used in language with dependent types, but also used in Haskell that has not dependent type. It has a powerful type system, but it is not a dependent type language. We will follow an intrinsically typed approach where we encode the security system in a definition of the abstract syntax. So terms of the programs will represent abstract syntax trees simultaneously with proof terms of the type system. And doing so, programs are secure by construction, and even better, such verification is reduced to type checking. Okay, we assume a bounded lattice of security levels with two operations, meet and join, and two values, top and bottom, that denote the highest security level, for example, public data, and the lowest security level. For example, here we have a lattice with 4 security levels. And we assume in a scenario where each variable has associated a security level, no? That states the degree of information that it stores. For example, we will have low variables and high variables. Okay, to see quickly the wild language, it is composed by expression and a statement. As expression, we have integer and Boolean values, identifiers, operations over Boolean operation and integer operation. And we will have a declassified expression that is used for declassifying the security level of expression E to L. And as a statement, we have an skip, assignment, sequence, conditional, and while. The semantic of this language is completely standard. The only non-standard expression is the classify, but at semantic level is equal to E. Okay, I will just present an informal definition of information of the security property, the limited release. Intuitive, this property expresses that only explicit the classified information is released and no other information. It's established that a program is secure if update to variables that are later declassified, occur in a way that does not increase information visible by the attacker. To clarify this property, I present an example. This is a simple program used for calculate the average of the salary of an employee. Suppose that the variables h1, hn store the salary of an employee. So since these variables are high variables, confidential variables, to store it in a public variable abc, we need to declassify this information to low. But an improper use of this program is the following, where we have a leak from variable h1 to abc. No? As you can see, the final value of the variable abc will be h1. Okay, the type enchantment of the security property, the type system of these are the following, where the first statement for expression means that expression E will have security type L under the environment gamma with effect D, where indeed we will store, the type system collect, the variables that are declassified in E. And for a statement, we have this type enchantment that means that the sentence is S, type in a program counter PC under the environment gamma with effect U and D, where the type system collects in U the updated variables and in D the declassified variables. Here are the typing expression for expression of the language. For example, for variables, the security type will be the type associated in the environment. And for the declassified expression, the security level will be the level L1. And the set of variables that are declassified in this expression will be the variables that are in it. Okay, and the idea of implementation is that this type enchantment will correspond to this type enchantment in Haskell, where an expression will have encoded in its type the security level and the set of declassified variables. And to implement the expression of the language in Haskell, we use generalized algebra type available in Haskell with annotation. And this generalization is over the return type of the constructor that must be the type being defined applied to arbitrary data type. And this feature allows us to encode invariant at type level. Okay, we will have a constructor for each rule of the type system. In a dependent typing language, this data type can be written easily, but in Haskell, types cannot depend on values. So, for example, the type S cannot depend on the empty list or in a low value. So we must leave values to types, and we must operate on a type level. So in the next slides, I will show how to programming at type level in Haskell to complete the implementation. Okay, the first extension that I will use is promotion. For example, for representing the variables, we use For representing the environments, I define I will use natural numbers, the variables of the languages, and we define the type S type for representing the security types of the variables. In this case, I just consider two values, low and high. And the environments is just a list that associates variables with security types. And to list these values and types to the one level up, we use the extension promoted data type. With this extension, the data type being defined, NAT and S type, are promoted to kind, and the values 0, low, high are promoted to types. The constructor sub is promoted to a constructor on type. To distinguish these values from types, we use quotes. So, for example, quote low and quote high are types that have kind S type. And the other constructors that are defined in Haskell, for example, the constructor for list, the constructor for page, are also promoted. Here, for example, this is the constructor for page at type level, and these are the constructor for list at type level. Okay, the other extension of Haskell that we will use is type family. Type family are used for defining function at type level, or similarly to defining parametric type. For example, for looking up the security type associated to a variable in a given environment, we need a function lookup. So we define a function that it operates on time. Here you can see that this is the constructor const for type. This is the constructor for pairs on types. The definition is by pattern matching. And the word family here distinguishes this function from ordinary function in Haskell. And the other functions that are also defined as type family are, for example, join and meet, that are the operation over the lattice. Okay, and the other extension we use is singlet to time. A singlet to time definition, in this definition, each type in the definition has exactly one value of that type. So, for example, another way to represent security type is with this data type that has two values, L and H, and the type of L is C type, quote low, and this is the unique value of that type, and the type of A is C type, quote high, and it's also the unit value of that type. So, doing pattern matching at type value, at runtime, what is the type of a value. And we will use this data type definition, for example, the constructor tag that is applied to an expression and a security level. And this security level is the security that must have the whole expression. So we need a copy of this value at that level. We also need to define the type nav as singleton type. Okay, and before we present the security type for a statement, I will give the goal of these rules. And first, the first goal is to prevent improper information flow during program execution. And this flow can appear in two forms, explicit or implicit. Explicit is where the information is copied to less confidential variables. For example, in this example, we copy in the variable L, which is public, the variable of H that is a confidential variable. Where implicit arises from the control structure of a program. For example, if an if statement or in a while statement. For example, in this example, if you expect the value of the variable L, you can infer which is the value of H. And the second goal is to control the information that is declassified, the information that is released. So here are the rule for the statement. I will not mention every detail, but I will show some of them. For example, in the assignment rule, we can see this contract, we can split this contract with two contracts. The first one says that the security type of the expression L must be less or equal than the security type of the variable. And this condition is used to prevent explicit flow, while the other condition that says that the program counter is less or equal than the variable is used to prevent implicit flow. For example, an assignment to a low variable must occur in a low context. In the if and while rule, there are also contracts for preventing implicit flow. For example, here, the type level of the expression if must be less or equal than the program counter of the branch, the code of the branch of the conditional. So, for example, if S contains a low assignment, then the security type of E must be low. The other goal, that is to control the information that is declassified, can be seen here. For example, in this rule, in this case, the variables that are updated in the statement S cannot be declassified in S prime. So we had this constraint. Okay, and to represent these variables in Haskell, I will use the same idea. In this case, this security statement will correspond to this security statement in Haskell, where each sentence will have annotated in its type the program counter, the set of updated variables, and the set of declassified variables. Here we also use generalized algebra data type to represent the statement. Each constructor will correspond to one of the rules of the type system. And okay, we use promoted data type, we use family functions. We also need some contrast. For example, this contrast means that this type is equal to this type. So the updated variable in the first sentence of a sequence intersection the classified variables must be empty. And this contrast is to ensure that the level of the variable, the expression of the assignment must be less or equal than the type of the variable. Okay, we have the other rules that are just translation of the rules. This is a class that model the order of the security types. You can see that this class have no method. We are only 20 in the instance. Okay, and can be generalized to a lattice of many security types. And to construct the environment of security variables, we use the following data type definition that is also a Sigleto data type. Here we use the constructor promoted to type for list and for pairs. For example, we have three variables that are natural numbers. We define in M an environment with three variables. The first one has associated the security type L, while the other one will have security type high. Okay, the constructor that will provide to the user of the embedded language are the following. Since we follow a deep embedded implementation of the ADSL, the constructor are trivial. They are just a constructor of a data type declaration. The only non-trivial constructor is var, but we receive as arguments the environment that we use it to type the expression. So with this constructor, we will introduce the environment in a program. And now I will show a use of this embedded language. For example, I implement the example given at the introduction. First, I define an environment with 4 variables. In the variables 1, 2, and 3, we will store the salary of the employee, and this is the code where we calculate the average of these variables and store this information in a public variable 0 by declassifying. And this is the improper use of this program that in this case is used for leaking information from H2 to the variable 0, which is a public variable, and is rejected by the type system of Haskell. So, a conclusion, we presented an embedded domain-specific language for information flow security in Haskell. This embedded language guarantees that well-typed program satisfies the security property delimited release, which is less restricted than non-interference. The implementation follows an approach where the code where we encode the security type system in a definition of the abstract syntax. And this approach requires a syntax-directed formulation of the type system. I didn't mention it before, but we need to transform the type system for being syntax-directed. And in implementation, we use some Haskell extensions that allow to codify invariants at type level. We can only write terms that correspond to secure programs, and the verification of that reduced to type checking. Programming at type level in Haskell is a bit tedious, so an important aspect of this language is that the user of the library does not have to program at type level. No, the examples given can be translated easily with that program at type level. So thank you very much, and if you have any questions.
So thank you very much for this pretty deep introduction to Haskell to me first, and also your contributions. Do you have questions? Yes, Lucas?
I understood that my question is why Haskell? So, but I want to explain why I'm asking that, because I understand that for your approach, you need a strong type language, you have an explicit type in Haskell, strong explicit type in Haskell, but you don't have it's a functional language, you don't have variables, right? And you have to define a way to specify variables there in your approach, right? So, wouldn't it be more appropriate to choose another language instead of Haskell, or then why Haskell? Basically?
Yes, we choose Haskell, which is a general purpose language. Of course, this implementation in Agda, for example, is trivial. It's more trivial than in Haskell. Because it has dependent types. But the idea is to provide a library or an embedded domain-specific language in a language that is general, that is with other purpose, with general purpose.
Other questions?
My question is quite similar to the Lucas one. I was thinking that if you are trying to work with types, it would be easier to use Agda or something like this that is related to Haskell. And
yes.
It's more easy to treat types.
Yes. Agda can be used as a language, as a functional language, but it's more used as a proof. But Haskell is used for everything, so we think that it's more usable for a user to have this library in Haskell. We use a similar approach for the formalization of education, and in here we use ALTA, but it's just a formalization, not a library.
I just have a naive question. How would encryption fit into that framework? Naively, I would think that the possibility to encrypt allows you to make some data travel, like some high security data travel on a low security channel, for instance. As long as it's encrypted, that's fine. Is that something, like, is encryption, the encryption, something that you can add to this model, or simply code into it as ways of changing the security levels?
I don't know if I answer you. Yes, to increase the security levels, we can define a class with methods and to manage it, and can be done easily. It's not a problem. Yes.
Anyone else? I do have a lot of questions, but I will ask only one. Did you manage or plan to evaluate this approach on real-life examples?
Yes, I have present just one example because I don't have time, but we make a lot of examples, for example, power checking programs, and all the examples that we take from the literature can be translated easily, without problem, and secure projected.
The reason I was asking before is, for example, I know that Facebook's owner Meta is doing something like this with their airline, and they found a lot of bugs actually. So this would be really interesting to see in practice.
Yeah.
If you can access something similar to that.
Yeah, thank you.
Okay, thank you very much, and let's thank the speaker again.
Right, so I'm going to talk about this framework that we have been building. Yeah, essentially it's called ULKB logic. It's a Python framework for reasoning over knowledge graphs. And it has two main goals. The first one is to provide a language and interactive environment for representing common sense and linguistic knowledge. And the second is to ease the application of state-of-the-art computational logic to reason over knowledge graph. I'm going to detail this. I'm going to give more details about this later. But a little bit about how we try to achieve those goals. First, I'm talking about plus interactive environment, and one natural choice for this is the logic. So in this case, we adopted the same dialect of Hall that's used by the Hall family, in particular Light, which is a popular interactive prover. And again, inspired by Hall Light, it was implemented as a Python library, right? So you have this language and environment as a Python library. About the knowledge graphs and the integration of computational logic tools, in particular external reasoners, the framework provides a graph API which allows you to fetch statements from knowledge graphs using SparkQL, which is a standard query language for RDF. And The framework also allows you to use external provers to prove things within the environment and using the knowledge that you extracted from the graphs. Under the hood, we are currently using the eProver and Z3, right? And why this is important? We believe there are few works that try to mix these two things, right? Of ITPs and the world of knowledge graphs. Okay, moving to the language, the logical foundations behind the frameworks. Essentially, again, is a Python library for building expressions in a type classical higher order logic. In other words, it's the language is a version of simple type theories extended with polymorphic types, which is essentially the core language of Holite. And the logic comes, it's implemented above this, right? So you have the usual logical connectives and quantifiers are defined in terms of this core language. This is nothing new, right? It's something that most Hall-based provers use. You have this core language, which is really simple, then you define the logic above, on top of this language. It's a type language, so you have a syntax for types, right? Essentially, you have the Boolean type to represent formulas. You have function type to represent function spaces. And of course, in this case, you also have type variables. You can have types, variables that represent arbitrary types. And under the hood, actually, most of these are actually constructed as type applications, right? You have a type constructor, you apply to some type arguments, and one of the constructors, the Boolean constructor, the other is the function space constructor. Okay, the terms are the usual terms of simple type theory, right? You can have a variable, you can have a constant of a given type, same thing for variable. You can have the application of a function to an argument, or the abstraction of some variable over some type. In Python, how does this work in Python? Well, you simply import the library, and then you can start building expressions using this simple language, right? At the line 2 there, I'm declaring a type variable. Then I'm constructing a constant named K of type A, then a variable X of type A again. And now I'm going to build a function, right, an abstraction. So this is the identity function, right? The function that takes an X of type A and evaluates to X itself. And if you can see there, you simply use Python to build these expressions, and you can print them, serialize them, etc. And at the last line, not the last, line 8 there, I'm applying the function I just defined to some argument, in that case K, right? And I get as a result an application. There's no evaluation here. I'm just constructing terms. Okay, naturally the next question is, okay, how do I evaluate things? Well, in this type of system, evaluation actually is implemented as an inference rule. Right? So you have that beta conv rule there for beta conv that you can apply to some beta redex, which is a term that can be reduced, which is the case of the term above, right? I'm applying function identities to some argument, and naturally the result of evaluating that is the argument itself. And as I said, this is implemented as an inference rule, and what you get as a result is not the value, you get a theorem, right? So you get a theorem that says that application equals K itself. Okay, this rule in this system actually is not a primitive rule of the system, it's a derived rule. And this is more or less the way that inference rules are implemented. They are functions in the meta language, Python here in the case, that allows you to build a theorem from a given input. Following the LCF approach, again, which is nothing new, it's most of the ITPs use this approach, you enforce soundness by restricting the privilege of creating these theorem objects to a core set of rules. Right? The core set of rules here is essentially the same rules that are used by Holite, so this time implemented in Python, right? I won't go through them, but it's essentially a sequent calculus with a theory of equality, right? You have a bunch of formulas on the left side, you have one formula on the right side, and most of the time this one formula will be an equality. Okay, talking about equality, I mentioned a lambda calculus. Now I'm going to show, not in details, but how logic is defined on top of that, right? So there is one primitive undefined constant which is equal, which is a polymorphic constant that takes two arguments and builds a formula, the equality that asserts the equality of the given argument. In Python, it's the same thing. You can use the constructors to apply this formula. For example, if you take equal and apply to k and k again, you get that formula, k equals k, right? That equal sign that appears there is just a notation. Below under the hood, what the term is actually equal applied to kk. Okay, this is the only undefined constant. The other constants are introduced by definitions. Again, nothing new here, right? It's standard stuff. For example, the constant true is introduced by that definition. The show definition is a command that you can run in the system, and it will show the definition of the thing you're searching. In that case, it's true. So true is defined as the identity function equals identity function, right? And why this definition? Well, it is not important. The important thing is that it behaves as true. I can prove it, right? And you can use, and this is below, if you take this definition, again, the definition is actually appearing on line 22, right? It's a theorem, a non-creative theorem that introduces the constant true. If you use this definition plus the inference rules, you can essentially remove one of the sides, right? You get true. So you just proved true. Okay. The other constants are introduced similarly, right? You have definitions for the connectives in quantifiers. You actually end up getting introduction and elimination rules. Again, is a sequent calculus. And one thing that I think it's a nice thing here is that you get a uniform way of representing all of this complexity, right? For example, binders, quantifiers are represented by high-ordered functions. But at the Python level, where we offer macros that hide this low-level stuff, right? So you can write as if you were writing a quantifier, but behind the scenes you apply in a high-order function. Okay, that was the language. Now I'm going to move to knowledge graphs and external reasoners. So about knowledge graphs, the library comes with an API that allows you to query a knowledge graph. And these queries are actually logical formulas. The API essentially consists of 4 functions. You have there ask, for example. You give it a logical formula, and it tests whether some instantiation of this formula occurs in the graph. The formula here usually is a formula containing 3 variables, right? So you want to see if some instantiation of this formula occurs in the graph. Select is similar, but instead of just returning true or false, it gives you the instantiations, or all the instantiations. And construct, again, is similar, but instead of giving you the instantiations, it gives you a formula, right? That P there is a template that can be used to construct a formula. And finally, pets, with some normal operation in knowledge graphs, where you give it 2 constants, and it tries to find pets of in this the graph. Behind the scenes, all of these are translated to Sparkle. Right, I'm going to now show a simple example of how we can use Wikidata with popular knowledge graph to construct a logical theory about some statements, which I'll show. So the first thing you need to do is you need to configure the library to talk to the Wikidata public endpoint, query endpoint, which is done there. Then you need to declare some vocabulary, right? We want to write questions, write queries, not just logic, right? So this is the non-logical vocabulary I'm going to use here. Knowledge graphs are essentially nodes and edges. The nodes represent concepts, the edges represent relations, right? So the concepts that I'm interested here are actor, blonde hair, female, Porto Alegre, which is a city in Brazil, and singer. And the relations are date of death, gender, hair color, occupation, date of birth. All of these are introduced as constants in the current theory. Let's say the individuals, they have a type A, and the relations, they have a type binary relation on A, right? Okay, with this vocabulary defined, we now can actually write queries, write logical formulas. For example, I have a formula there that says that represents a query. It has a free variable, actually, one free variable x. And what I'm trying to find here is the axis such that The gender is female, the place of birth is Porto Alegre, it's either a singer or actor, does not have blonde hair, and has some date of death. Okay, it's a complicated formula, but not structurally, right? Now, how do I use the API to actually find instances of these formula in the graph? You simply, is I'm using construct, right? So I'm asking for 10, at most 10 instances of these formula in the graph, and each of these is returned as F there, and I take this formula and add it to the current theory. So I'm extending my theory with new axioms that come from weak data. If I ask the system to show one of the axioms that was introduced, you can see this one here, and it says that Elis Regina is female, her place of birth is Porto Alegre. In other words, Elis Regina fits, right? It matches the X that I was searching. It's one of them. One thing to note here, I could use the deductive system already to prove something here. For example, if I wanted to prove that the place of birth of Elis Regina is Porto Alegre, I could just apply end elimination to this formula and get this result. But I will show that we also can use external provers to do this. So, for example, in the code block below here, if I want to prove that the place of birth of Elis Regina is Porto Alegre. To prove means to construct a theory, a theorem. In this case, I'm using this rule Z3 here, right? And it returns a theorem. And what does it mean? Well, it means that Z3 was able to prove that from the current theory, right? We have this inference rule here, which is a special kind of inference rule, which takes a first-order logic formula and then uses the theory you have so far, at least the first-order part of that theory, and tries to prove this sequence here, right? That the theory entails the formula you're trying to prove. If the tree is able to come up with a proof of this, then you get a theorem. If not, then an error is raised. The same thing, the same interface is used for E, right? You simply have a rule E that behaves the same way. For example, suppose we wanted to prove that Elis Regina place of birth is Brazil, right? Which is something that's not possible because we don't have nothing about Brazil in the theory so far. If you try to prove that using rule Z3, you get an error, right? It's not possible. But one way to do that is extend the theory. So for example, here I'm showing how you get some axioms about Porto Alegre from Wikidata again, right? In this case, I'm getting the paths of length 1 linking Porto Alegre to some entity, right? At most 200. And I get a bunch of axioms. One of them is this one. The country in which Porto Alegre is located is Brazil. Okay, this is a hint, right? Okay. The next thing I need is something connecting place of birth to country, right? And this comes from common sense. And how this ends up here, it depends on your system. You can write this. You could try to use a, I don't know, LLM to generate something for you. I don't know. And what this axiom says is that, okay, for all x, y, z, if the place of birth of x is y and the country of y is z, then the place of birth of x is z. It's something obvious, right? And now if I try to use Z3 to prove this, Z3 is able to prove it because I have this axiom and because I know that Porto Alegre is located in Brazil. Okay, I'm almost at the end. Talking about related works, well, interactive are obviously related. Applications of logic to knowledge graph, most of them deal with automated reasoners, fragments of first-order logic, and very few works that try to apply higher order logic in an interactive environment to knowledge graphs. There are a couple of few of them described in the paper. So, quick conclusion. We believe that this is a step towards combining computational logic tools of not only the interactive ones, right, because the interactive can use the automated ones, with knowledge graphs, and this is important if you need to deal with common sense, for example. So far, our focus has been knowledge graph and reasoners, but of course, there is much more to do. There's something we're completely ignoring, mathematics, at least the axioms about or theories, mathematical theories. how to deal with large theories, how to interface with other provers. In this case here, it would be really interesting to interface directly with Hall light, because Hall light has all of this, right? And finally, applications. I didn't mention any application here, but just a quick note. Something we're doing right now is we're using these framework to represent English sentences, at least their semantics, right? And with these two things, we can fact check and check the reasoning of text produced by language models, for example. And that's it. Thank you.
Thank you very much. Is there any questions from the audience?
Thanks for the talk, interesting work. So do you support only RDF graphs? Is that it?
Yeah, currently RDF.
So, for instance, if I have a knowledge graph in Apache Gina, I can connect to your work somehow, and but in order to provide these statements, I was thinking about, because you have to define the constants for the theories and everything. So maybe if you already have the knowledge, infer that and then just specify the actually the purpose of the query instead of having to define all of these constants. So
actually, there's you actually need the constants if you're going to write them in Python, right? But if you check the results here, for example, I don't know. Okay, Elise Gina was not defined, right? So I got a constant here, which I know it's of type A because this is a constant, right? In the knowledge graph, it's not a relation, and was returned here. So actually, you just need to define things that you're going to write about. Answers will bring new stuff.
Others?
I'm just trying to understand what you just said. If I then ask for the existence of something in the knowledge graph, I would assume that the system can come up with something that I haven't explicitly listed myself. Is that correct?
You're talking about an existential query of the type, does this hold?
Is there somebody who was born in Brazil? Can I ask that and then have something returned to me that I didn't model as a...
Yeah, there's a subtlety here because the link between what happens in the graph and your theory is done by you, right? At the application level. For example, here I explicitly took the formula return and added to the theory, right? So you'll have the information, true, yes, something exists, but you are responsible for doing something with that information that affects the theory. I don't know if...
Okay, and my other question is, this is an open world, right? If I wanted to prove that, you know, every person named Edgar was born in Brazil, for instance. It may be true in my knowledge graph, but I don't know if my knowledge graph doesn't necessarily represent a complete word, a closed word, right?
No, yeah, but essentially what you from knowledge graphs are instances, right? Formulas. This kind of thing, you have a quantifier, then you need in your to prove this kind of thing.
I think it's related to this question because most of RDF knowledge graphs are based on ontologies, right? So you can specify using OWL or stuff like that. So do you have, and you can reason on OWL and check properties there as well. So is there any relation?
We have support for
how to link ontologies to what you're doing as well.
Yeah, I don't have an example here because this is really a simple example, but we have support for OWL in the functional notation. And what we do is we read your ontology, we translate it to first order, and we add it to the theory, right? And then the problem is yours, right? What do you do with that? Yeah.
I also have a question related to this. I admittedly didn't get everything that you said, but at the end, when in your conclusion you manage some application areas, I guess it sheds some light on why you would do this.
Yeah.
So what do you get from combining, what do you get from this that you couldn't get from Sparkle, for example? Could you restate this?
From Sparkle, well, Sparkle is just a query language, right?
I know, yeah, but I mean, the example is mostly like, could be done by query. Right?
Yeah,
I could infer that Porto Alegre is in Brazil, and so I could do this with Sparkle.
Sure, yeah, you could, or with a traditional reasoner. But I think that the key idea here is provide an environment where you can, you know, merge all of these things. Not only something that works just for RDF or just for I don't know, DL or something like this, but something where you can connect other things like theorem provers, for example, or SMT solvers. It depends on what you're trying to do, really. I mean.
Can you go to the last slide?
Sure. This one.
Yeah, so large theories, yes. So this is what I would think, and I would like you to confirm or refute my assumption here, that if I have a knowledge graph and there are implicitly connected things there, right? So for example, I know I can derive from math, or I can derive from some theory that two things are connected, but this is not in the graph. That's what I would use your tool for.
Yes, yes, or maybe the graph is too large, you know, for simply ingesting it, you know.
I see.
With data, for example, 1.5 billion statements, right? It's not going to work, and most of it, sometimes this statement can be contradictory, right? So it's probably not a logical theory. I mean, a sound theory to just translate the graph into a bunch of logical statements.
Thank you. Any other questions? So, actually on schedule. So, the stage is let's finish there is a lot to do, so probably you can find what makes you happy and what makes the world examples for promising formal verification algorithms and approaches that could be applicable in this field. So, acknowledgements and a couple of disclaimers. So this material is based on the specifications, which were produced by the SysMLv2 submission team. All the people I mentioned, it's impossible to enumerate them, but this is not a one-man show, as I said. Also, some presentations from Konrad Bock, Ed Seidowitz, Sanford Friedenthal. These are people working on SysMLv2. Actually, Sanford Friedenthal and Ed Seidowitz are the chairs of the whole specification process, and some of my colleagues from the research group, and also some of the working groups from the newly formed systems modeling community. So disclaimer, these are work in progress. Okay, so the beta specifications are out, but we are not done yet. So what you will see is really an overview of where we are now, and any question that you might have will probably be a good question. Okay, so I will try to answer, but sometimes there are no answers yet, and then you are invited to come and ask your questions. Okay, here, okay.
Stay right where it says, might have the website. That is the website others are, you stay in front of that.
Where?
The right.
Here, so shall I go here then?
Yes, perfect.
Okay, excellent. Yes, so let's start with model-based systems engineering. Okay, this will be a very short tutorial in a nutshell. I'm perfectly sure you are aware of critical systems. This is our main motivation of working with any algorithm, right? Because math is nice, but if you want to get a paper submitted, you have to give a good motivation why this will help the industries. This is the same with systems engineering, but what I would like you to change now is that we should stop for a second looking at these things breaking all the time and thus coming and helping, preventing these issues that kill people and stuff. Let's just think about the management aspect of such systems for a second. So if you want to design an airplane, what amount of data or components or stuff you have to deal with. We will go a little smaller and just design a car. So in a modern car, you have about 20,000 parts. These are not even the small parts, not even electronic stuff. These are things that you can identify and order from other companies. About 1,000 main components, which, for example, the chassis, and hundreds of subcontractors. Okay, so this is not done by you or your company. It's a cooperation between several companies who rarely talk to each other, right? So they have their orders, and then something gets shipped. So what you can do in this industry is to be a top-tier car manufacturer. It means that you are actually not going to produce most of the car, you are just assembling it. So you will specify what you want to have. For example, what kind of steering system you would like to build in your car. Another company will produce this, but of course they will not produce the electronics for that. So another company below them will produce the electrics, and below them somebody will supply the silicon and stuff like that. Okay, so this is a very hierarchic layered structure of companies working together, and on the top you can actually hope for the best, right? So you give a specification, you describe as precisely as possible what you want to see, and when it gets shipped, you just assemble it and see if it works the way you intended. And this, of course, cries for modeling, because then you could virtually assemble your car before getting the components. You can decide whether your specification is okay or not. And if you're sure that your specification is okay, you can be a little bit calmer that by the time you get your very expensive components, everything will work together. Okay, so some things that we came up with recently that can complicate this a lot is, for example, drive-by-wire. So we are dropping mechanical connections from everything, right? Because it's not flexible. It's trustworthy and simple, but it's not flexible. And instead, we put software, right? So we have electronic control units in a car. You actually have 50 to 100 electronic control units. These are small computers. And on them, you have a lot of software, 100 millions of lines of source code, for example. And you produce a lot of cars running these softwares. You have just a little chance of making a mistake. Some of those cars will break down, probably cause an accident, and so on. Okay, so we are making this really hard, and software is not easy to debug. I guess you are all aware of this. So the consequence of this, as I already hinted, is that it would be nice to have some detailed design, very precise detailed design, some early analysis, even before giving out the specifications to the subcontractors. It would be nice to simulate the whole thing before getting the test driver out on the street. And of course, I would like to see why I did something. So traceability is about tracking the reasons, the design decisions, why this is there. Why did I say that it would be enough to have 200 kilograms of something? Okay, so this is the goal. So what do? We model. And this is quite elementary, but I really like the animation here, so let's go through this. What is a model? If you go on Wikipedia, of course, where else you would go, you would find this very helpful sentence, right? A model is an informative representation of an object, person, or system. Okay, a little bit more informative is that a conceptual model, which we are usually dealing with, it's not a physical model, it's a conceptual model, is a theoretical representation of a system, which consists of concepts used to help people know, understand, or simulate a subject the model represents. Okay, so now we see there are some purposes here. The term may refer to models that are formed after a conceptualization and generalization process. So now we see how we build the models. Conceptual models are often abstractions of things in the real world, whether physical or social. So we want to represent something in the real world. And finally, there are semantic studies, which are relevant to various stages of the concept formation. Semantics is basically about concepts, the meaning that thinking beings give to various elements of their experience. Such a nice definition, right? Okay, so what is a model? I can give you a very spectacular demonstration of what a model is. This is a model. Actually, I lost the animation. They were supposed to move around and the text rearranging itself into a model. Unfortunately, we won't see that. But this is the same thing from the text. from the same words, but I would argue that it's a much cleaner representation, right? So you can just put your eyes on one point and immediately see what are the relationships between elements that you defined. You can even categorize these. So you could probably spot that all the boxes were colored. Actually, this part represented reality. This is the model, this is the modeling language, and we also defined or spoke about some kind of methodology. And if we just think about this a bit more, actually, what is a modeling language? A modeling language is exactly this, categorizing your modeling elements, right? A type of a modeling element is the language. If you think about it this way, basically everything down here is instantiated in your model. And when you speak about element of reality, you can say that the system is a kind of element of reality, and then you specify the relationships with other concepts. So here we arrive to modeling languages. Of course, this is also called a meta model. This is probably more familiar to some of us. So there is another important concept, which is important in model-based systems engineering as well, is abstraction and refinement. Again, here, this is quite well known, probably. So on the abstract or the concrete end, the most concrete thing I can have in system engineering is the real system. There is no questions there, right? On the other end, there is something like it exists. So I think about something, and it would be nice to have something, but I don't really know anything about it yet. And somewhere in between, you have a high-level model, which details some of the concepts that you want to build, and then you go into low-level model, and if you're lucky, after some time, you will arrive at a concrete system, right? And if we think about this from yet another perspective, this kind of refinement is actually the design process. So what you do here is that when you're here in the very abstract, there are a lot of systems which fit your specification, which is very, it contains very little details. So many systems can fulfill what you imagined. And then you start to be more precise, because what you want to achieve is not just some other system, you want to be inside your requirements. Your requirements will also determine a set of systems which are valid in a sense. And what you want to do is to start from somewhere out here, and with small jumps that we call design decisions, we want to arrive to the desired system, which is hopefully in the set of systems satisfying the requirements. So what do we do when we design? I state that first we want to find the relevant features of the real world. This is called conceptualization. We want to have concepts to work with. We want to say there is a car, it has wheels, it has a steering wheel, and so on. And then we identify constraints and requirements. This is refinement, because we want to specify how these concepts should relate or how they should be. And then we make design decisions that gradually start satisfying more and more constraints, right? So at the end, this is basically documented thinking. So what I would like you to see is that modeling is documenting the way of thinking, and it should really contain the path that led to a concrete solution. All right, so probably you are very well aware of the V model. This is one of the most basic workflows to build safety-critical systems. And from a systems engineering perspective, we are interested in the top 3 levels, right? So when I'm designing a system, I want to come up with requirements, have a functional specification, design some architecture, and then somebody else will ship the components. So another point of view from the systems engineer is that as you go down in the V model, you will have more and more subsystems, components, hardware, software, and so on. After some time, you will stop caring about details. So this is already the component design. But what is useful in this world still is that this part up here can be the single source of truth. And this is something that is, getting more and more important. A systems model should be a database of everything, all your design. Even if you have other models to analyze or component realizations, implementations, and so on, they should point back to something in your system's architecture, or results of your analysis should be back annotated into the system design, because that is where you store all the information that you have to know about the system. And then you can query it, and then you can verify stuff, and so on. Another aspect of having a good system architecture and being a system architect is that you have to do this kind of haggling, right? So you're a car manufacturer, you specify components and then you integrate them. What happens if you, for example, said that two subsystems will have a certain contract? What does that mean? It means that the subsystem promises something. Okay, so this is a requirement that I specify for a subsystem, and on the other side of the contract, it will be an assumption. The other subsystem can assume that this subsystem will behave nicely. What happens if we get a guarantee from this component which does not match the requirements? So somebody says that it's impossible to do this. I mean, it's a nice specification, but nobody will ever ship that. So what you can do here is that you have a complete view of all the system, and you can see if there is slack somewhere. There is an opportunity to refine an assumption. For example, you can ask the other component, because now you don't have the contract, you can ask the other component if you can do this with a slightly modified assumption. And most of the times they will be able to do it. And you can propagate these violations around your systems architecture, and hopefully you will arrive to a more or less optimal solution. So these are all the things that systems engineers are generally concerned with. Of course, this is a brutal simplification. And there are a lot of processes that can guide you how to come up with a system architecture like this. I had the impression that in Brazil, the Arcadia methodology is quite popular. Have you ever heard about Capella and Arcadia? Okay, it's not very popular here. Anyway, this is a procedure that can give you guidance on how to refine your model up to an implementation, starting from the requirements. There are other methodologies like this. For example, the platform-based systems engineering, which separates the functional model where you speak about what you have to do, and the platform model, which specifies what can actually achieve this. But what I would like to point out here is first the traceability that I already mentioned, and the central question here is I should be able to answer why I designed something like that. And for this, you need the design decisions, you need your, all your data. You need data from your simulations, some kind of analysis, verifications. You should put that in your model and point to it that, hey, this is why this part of the model looks like that. Okay, so this is one thing which we could be responsible for in formal methods. And then, of course, you can check a lot of things if you follow these traceability links, because you can verify that the decisions were actually justified. And the other important aspect is verification and validation, and now we are approaching the topic of this conference slowly. Here you can speak about three different areas. Verification and validation, I think, is a bit confusing because we use validation for different things. So what I would like to introduce here is that we have model validation, which is about whether your models make sense or not, or complete and consistent or not. So this is about your model versus the modeling language and constraints on that, while system validation is about checking whether your system performs as intended by your clients. So this is the final step before shipping the product. And verification is about checking whether what you're doing is correct. So you manage to refine the previous step of your design, or you are still correct after introducing all these extra details. Okay, so where can we use formal methods in all this? This will be the next very short topic. First, this is where we define the modeling language. We can ask a couple of questions here. Did we use the language correctly, right? Because most of the modeling languages will have well-formness constraints, which are sometimes first-order logic or equivalent queries. You should be able to find patterns in your model violating some constraint. You can also check if the language is consistent. This is much harder. Actually, there is very little literature on how you can check if a language makes sense, because you need to be aware of the purpose, and so this is very hard. If we think about abstraction and refinement, we can check if the refinement is correct. So this is very well known in formal methods. When we do the design decisions, of course, we can check if we meet the requirements. This is the classical formal verification. You can check if your design decision was correct or justified. This is almost like witness validation. So there are a lot of things that you can put on this map. And of course, in the V model, you can generate test cases, generate scenarios. You can use model checkers to do this or some other method, abstract interpretation, etc. And you can check the conformance between higher level models and lower level models. Okay, so these are mostly the areas where people use formal methods. So what we would like to achieve here is to turn the documented thinking into documented and verified thinking, right? This would be a quite beneficial property if we are building safety critical systems. And this is how we will end up at the topic of this tutorial. Some more verification and validation techniques, but I guess I already mentioned these. You can have a lot of techniques applied on these challenges. And I will speak about graph queries a little bit. I will speak about model generators a little bit, but mostly model checking and mostly about the semantics of the language that we would like to apply this to, because most of the other talks in the conference is actually about these things. So we arrived at the SysML v2 language, and I will check my time every now and then at a glance. Okay, so how many of you know SysML? Excellent. So we can start with this then. What is SysML? I was expecting this, right? Eduardo yesterday told me that his talk will be funny because now he's not convincing AI people that formal methods is useful, but convincing formal methods people that AI is an interesting subject. I'm doing the same. I'm usually trying to convince systems engineers that formal methods is nice, and now it's the opposite. I would like you to see that there is a lot of things that you could do here, even more than we currently do. So what is SysML? This is the systems modeling language, which is basically UML for systems engineers. How many of you are aware of UML? Yes. Okay, how many of you like UML? Okay, that was much less convincing. Still, everything is according to my plan. So, so SysML is supposed to be an extension of the subset of UML, which is, by the way, every language in the world, but this should be a non-empty subset of UML extended, right? And basically, it has blocks instead of classes and components, because a block is a nice generalization of anything, any component that you can build in your system. And there is a stronger emphasis on modeling physical artifacts, because we are not dealing with software anymore. And SysML version 2 is actually the new version of SysML after 1.6. There is still 1.7, and probably there will be 1.8 as well. But version 2 is a complete redesign of the systems modeling language with a lot of new features and addressing some long-known issues. These pictures illustrate what SysML is in my eyes and what SysML v2 is supposed to be in my eyes. And it also coincides with the magnitude of the problems that the languages would like to tackle. So, an overview of SysML. This is actually 3 specifications. In this slide, I will list 4, but 2 of them are in the same document. The first one is the kernel modeling language, which is the new basis instead of UML. So we dropped UML, no more UML, bye-bye. It was actually a very constraining meta model, which made a lot of problems. So we came up with a new language, right? This is a good idea. By the way, Caramel is based on MOF, I forgot the abbreviation, but it's based on MOF, and MOF is based on UML. So, Meta Object Facility, thanks, yes. Yes, this is actually there was a meeting about this, I think on the last OMG meeting, whether they should make the kernel modeling language the foundation of a new UML. So UML 3, for example, could be based on the kernel modeling language, but that would be funny because the kernel modeling language is based on MOF, which is based on UML 2. So then UML 3 would be based on UML 2, which is not very lucky, right? So anyway, let's assume that this is not based on UML anymore because you will not recognize UML anywhere. But this gives a very nice foundation for new modeling languages, including the systems modeling language version 2, which is a separate specification that specializes the kernel modeling language and gives all the systems engineering concepts that people like to use. There is also a third document called Systems Modeling API and Services. Welcome to the 21st century when we are not only dealing with modeling languages, but repositories, tools, interchanging data, right? So this is finally recognized. This specification is about how you can access your models regardless of the tool you bought for a lot of money. So this is a critical point. And also there is a fourth document merged into this one actually, which specifies how you can transform your SysML v1 models to SysML v2. Because they recognize pretty early that if you have v1 models and suddenly you have to move to v2 and there is no guidance in that, no interoperability, anything, nobody will ever shift to v2 because you have your airplanes, rockets, missiles, cars, whatever, designed in v1, and it's not that easy to redesign them, right? And nobody would want to do that. So the objectives of the specification is to increase the precision and expressiveness. There is also a list of how this is achieved. In SysML v2, actually in the kernel modeling language, we are now grounded in formal semantics, and I will speak about this shortly. We would like to increase the consistency and integration inside the language, which led to a more consistent terminology. And finally, state machine activity diagram and a sequence diagram are not completely separate things, but you can actually use the same elements in different contexts. And this is quite refreshing if you have ever worked with SysML, right? That you can put something that happens in a state machine on a sequence diagram or the equivalent of that. So another very strong point is usability and extensibility. Modeling in UML and SysML is not always fun. It's actually quite cumbersome to do a lot of things. So they introduced the textual syntax this time, and you can even add your own keywords. So there are no stereotypes and profiles anymore. You can just define your own keywords and that's it. So a textual syntax is very nice because it's implicitly a carrying format. You can just use a text file to move your model from here to there, which is very convenient. Also, you can have syntax highlighting, content assist, static checks, a lot of things that are well known in programming, but are science fiction in systems engineering. So this is a very good thing. Interoperability was also a concern. This is why the API was defined, and as I said, the migration path from SysML v1 is also handled. So the language architecture of SysML v2 looks like this. You can see 3 layers here. The first one, the root, we do not bother with this. This is the structure of the language, packages, namespaces, and so on. It's quite boring. The core syntax and the core semantics defines the ontological basics of the language. This part has actually mapping to formal logic, to first order logic actually. So on the foundation of everything, you have first order logic. Some people are happy about this, others are not so much because you will not be able to prove a lot of things, but at least you have some logic somewhere underneath the language. The kernel layer introduces generic concepts building on the core. I will mention a couple of these. And you can notice that this is not a semantics anymore. This is the kernel model library. The library, it means that this is actually a set of elements composed of elements in the core. And the meaning of these elements are reused to the first order logic definition of the core elements. Yes?
When you say that you have this phrase you first talk about it first, does it cover everything that is in the syntax?
Everything?
Does it cover everything that is in the syntax?
Yes, everything in the core syntax. And everything above that will be reduced to the core syntax by composition and things like that.
The second question is, how is this phrase? What language are you using?
It's not LaTeX, but almost. Yes. This is something where contribution would be very nice. And I was thinking about this myself, but the effort required for this is quite large. So a mapping to some formal language would be really nice here. Was there a question there, John?
Is this first order logic or just some
I think it's full. So they don't really care about decidability and things like this. Unfortunately not. This is one of my biggest issues with this part, that this is very, handled very implicitly. The specification mentions something about how to use integers and stuff because they are modeled as data types, but their semantics are not defined in the core. I think there is an open issue about this. As I said, very good question, ongoing work. Feel free to contribute. Okay, and the top level is the systems, syntax, and libraries, which is SysML-v2 actually. There is another kind of layering, which is vertical here. So this one is the syntax, which we call M2. This is the meta model layer. Here we have the library and user models, which is M1, the model layer. And what you cannot see here is that M0 is the real or simulated instances. Okay, and these are in an instance of relationship, but I will speak about this a bit later. Anyway, these concepts, M1, M2, M0, these are quite frequent when you read about SysML-v2. Okay, let's take a look at the textual and graphical syntax. Finally, as I said, we have a textual syntax. It looks like this. You can actually see or smell Eclipse, right? If you're familiar with Eclipse, this is a very familiar syntax highlight, yes?
I don't know when is the best time to ask that question, but as I know of SysML, I also know of things called ADL with the green and also Lustre.
Yes.
And I was wondering if these are kind of comparable frameworks that are sort of different standards meaning, or if there's a different nature between those frameworks.
So actually, AADL is being ported to SysML-v2. There is ongoing effort to reformulate AADL on top of the kernel modeling language. So they will be compatible, and yeah, I assume that you can actually mix them at some point. Okay, so the advantages of the textual notation is that it's easier to write. If you have ever arranged diagrams, I actually wanted to do research like this. How much time do you spend out of your 8 hours per day organizing your diagrams instead of coming up with new ideas? I assume this would be a very large number, at least 50%. So now you don't have to do this, you just write your model, and there is actually graphical and tabular syntax, and right now in the pilot implementation, this is auto-generated, which is not always very nice because it uses GraphViz, and that has issues, but we expect that as soon as we have commercial tools, this will be much better. Okay, so another thing which is new compared to V1 is that there is a very consistent usage of definitions and usages, which means that a definition is basically a type or declaration or some kind of blueprint which you would actually use in your code as well, a class definition or something like that, and you can use these in different contexts. And that would be a role or a property or a feature, but not an instance yet. Okay, it's still not an instance, it's just telling you that in a car there is a wheel. This is using the type wheel in a certain context. And then when you instantiate the car, you will get the wheel as well. This leads to a very nice and consistent methodology. As you can see, the SysML-v2 side of this table is rather boring, and this is intentional. This is a big step forward. In V1, for example, you had part property as a usage of block, but action as a usage of activity, state as a usage of state machine, and so on. This was very inconsistent and hard to learn, and some of the things didn't even have usages. In V2, almost everything has a definition and a usage, and this facilitates reuse and refinement in context. The basic language elements after this, keeping in mind that everything has a definition and usage, looks like this. This is an ontology, right? So we start from a very generic type called anything. Anything, by the way, has things which are tied by anything. Now you can understand why it takes so long to speak about the semantics in this context, because when I say anything, it's hard to tell if I'm speaking about the type or whatever. So, but this is very generic. And after that, you have occurrence, which puts your things in 4D, in time and space. And then you can specialize that into objects, which are primarily in space, and performances or behaviors, which are primarily in time. And then a kind of object will be an item that you can pass in your system. It's like fuel or a message or something. And you can also have parts which are more sophisticated. For example, they can perform actions or they can have a state, something like this. Also, a behavior can be specialized into an action. And this was weird for me at first. I would be curious about what you think, that a state is actually an action in SysML v2. Can you see why? The change of state is also an action. Yes. So a state is basically an action of waiting for something to happen. This is the philosophy. And also a decision, by the way, because I have to decide which something I will react to. Yes? Yes, but only transitively. So this one is formalized in first order. This one is formalized on top of this and related things, and so on. So if you look at the specification of state in the model libraries, good luck. So you have to drill very deep to find the final mathematical formulation. And unfortunately, we are not there yet. So this is ongoing work. Where we are now is somewhere here. Okay, I always like to hear this. Okay, and you can see that there is a lot more. You can have constraints, which already spoils that finally there is an expression language. Again, if you don't use UML or SysML, you don't know this, but in UML and SysML, every time you have to specify a guard condition, you just put there a string. You can write anything in that string because it's not part of the language, right? Finally, we have an expression language, so you can refer to things, you can have integers, you can have operations, you can have anything you want. And this is a very strong basis for formalizing something, actually. You can have requirements, and since now you have expressions, you can actually formalize your requirements in SysML. It's not only words anymore. I actually have a slide about this, so let's continue. You can have objectives, you can have cases. We used to have use cases, but now you also have verification cases, analysis cases, trait studies, for example. You can model what you do with your models to verify that they are correct. Okay. Yes, so requirements. Requirements were really enhanced in SysML v2. They are more formal. We still have the textual description and we still have the ID, but now we also have attributes, which you can think about like a parameterized requirement. You have placeholders for things. For example, your vehicle should be less than something. That something, the max weight, can be, for example, a parameter, an attribute here. Yes, mass required here. And then you can specify in a constraint that your actual mass, which is also a parameter, is less than the required mass. And then you can have these formal constraints. It can be assumption or requirement. An assumption is necessary for the requirement to be a requirement. If the assumption is not met, you don't have to oblige the requirement, right? And you can also specify these constraints in third-party languages. So there is built-in support to include other syntax. Of course, we'll see what kind of tool support this gets. You can declare the subject of a requirement. You don't have to, but you can specialize what the requirement is about. Initially, the requirement is about anything, literally, that's the type. But if you say this is a requirement about a car, then you can actually bind your, or a vehicle, you can actually bind your attributes, your parameters, to features, to attributes of the car. And suddenly your requirement can be instantiated for a concrete car, right? So this is very nice to organize your requirements into libraries and to have a nice specialization tree, because now requirements can specialize each other, redefine features, extend some things. So this is very powerful. Okay, modeling, analysis artifacts, I already mentioned this. You have use cases, analysis cases, and verification cases. I guess we'll see this later. There is also variant modeling, because, for example, in the car industry, this is a very critical point. You can have a lot of different versions of the same car, basically little changes in engine or transmission or stuff like that. Obviously, you don't want to have separate models for each. You want to be able to say that this is where you can choose another kind of transmission. This is supported now with variation points and variants, and you can even have constraints about what kind of variants are compatible with each other, which is a very nice feature. But again, as a formal methods community, we can already think about, hey, this is a satisfiability problem now, right? So if I have well-formness constraints about how a vehicle should look, and I don't have the vehicle model, I just have variations, you should be able to check whether for all variations, you actually satisfy your requirements, your constraints, and so on. So this is an open topic. Okay, and we are approaching the core, the semantics part of this talk. So now we have a well-defined semantics. This is like 60% marketing. We are working on it. Because we have an expression language, as I mentioned, we have support for modeling instances, which gives you a nice opportunity to reason about, for example, counterexamples or execution traces or things like that. Execution cases are actually interpreted as a 4D instance. We'll speak about this more, but I wanted to plant this in your mind that we are, at some point, we are going to shift to 4D, which is always fun. And you can model temporal aspects. So for example, you can say that I have a vehicle which has a time slice which represents its assembly, and then there is a succession to the snapshot, which is the moment of delivery. You can specify the state of your car at that point, not exactly the state, a snapshot of your car, and then it will have several time slices representing the duration while it is owned by somebody. Okay. And I think this is the last feature I want to talk about with regard to the language, which is extension. So instead of stereotypes and profiles, we have metadata, which is quite generic. So you can have two specific annotations. For example, you can tell that this verification case is supposed to be verified with, I don't know, theta model checking framework, or tell me your favorite model checker. I wanted to come up with something that is not ours, but I failed. Anyway, you can have language extensions as well. These are also metadata. So for example, you can specify a domain library of your concepts. You want to extend the language. For example, you have scenarios which have situations, causes, and failures. This is about fault modeling, actually. And then you can say that you have a metadata called scenario, which is a semantic metadata, which tells the language that you should be able to use situation as a keyword. And whenever you use situation as a keyword, what you're saying is that this thing, which we now call power law, is a specialization of a scenario, and therefore you can use anything inside here that you defined in your domain library. You could have done this manually. You could have said that this is a part and it specializes scenario, but it's much easier and spectacular to see that you actually declare it as a situation. Yes, we also have reflection, which is quite funny in a systems modeling language, but also is very powerful. For example, you can use it to have package imports which are filtered by the properties of the elements. You can say that I want to import everything that has a speed, for example, and some other things. And this can be the basis of introducing new formal concepts. So if you have, again, a verifier or some kind of tool that can verify fault tolerance, for example, you can include your concepts in the language and allow users to use your tool's concepts inside the systems engineering model, which, as I said in the beginning, would be a nice goal. Yes? So, yes, I messed this up. So this should have been scenario. So these are cut from a file, and I'm sorry about that. This should have been scenario, yes. Situation is also in the example, but yes. Okay, the API, I guess we already covered this, and it's not very interesting from our point of view, except that this will be the entry point if you want to integrate with a SysML tool. You will be able to query the model, and hopefully you won't have to deploy your plugin to each tool that is out there. Okay, so you can find further information on this in the beta specifications. It's easier to find them by searching for OMG SysML v2, and then you will have an announcement which links all the specifications, but the links are not very hard to memorize as well. There are up-to-date documents and training materials on GitHub in an open repository. This is really cool. Anybody can go there. And there is a slideshow, for example, introducing the textual syntax and the graphical syntax as well. And there is a pilot implementation, which I would say is probably the best decision they have ever made. The specification is not only written in text. In parallel, the team was implementing everything in Eclipse and also in Jupyter, by the way. So there are 2 pilot implementations which prove that this is feasible. And actually, they quote a lot of bugs in the specification by implementing it and finding out that, yes, it doesn't work. Or we have a well-formness constraint, which is violated in the library, which should be the ground truth, right? So this helped a lot, and you can try it. It's not perfect, but it's usable. And there are other tools out there which are coming up slowly. Okay, do you have any questions about the language from a high-level perspective? I guess if you had, then you already asked. Okay, so we can now drill into the semantics. So the semantics is, at first I had the title Semantics of SysML v2, but this is really the semantics of the kernel modeling language, and transitively it is the semantics of SysML v2 as well. So if you understand this, you will be able to check whether your mapping to a formal language is consistent with the definition, with the specification of the meaning of, for example, a state. It will be hard, but it will be possible. Okay, so if you understand the basics, everything else is composed from that. Therefore, we will focus on this. As I said, the kernel modeling language is based on ontologies. So yes, actually, I will cross that out a bit later. So what is an ontology? Again, according to Wikipedia, this is in information science, an ontology encompasses a representation, formal naming, and definitions of the categories, properties, or relations between concepts, data, entities to pertain to one, many, or all domains of discourse. So what you have to see here is that there is a representation of things or categories basically in the world. Yes, I already said this, in the world. A little bit easier is to check this definition. An ontology is a way of showing the properties of a subject area and how they are related by defining a set of terms and relational expressions that represent the entities in that subject area. This is basically modeling. This is also ontologies. So you can see the logo of all here. Unfortunately, this is not all. Okay, so there were some ontologies out there, but the kernel modeling language does not build on any of them. It borrows a lot of ideas, but even the semantics is defined in a different way. Yes, we have to live with this for now. So let's start from the basics. I already mentioned the M0, M1, M2 levels. Here we will start by checking out which layer includes what. So in the universe, in M0, you have the set of all things represented here. And it's not only the entities in the subject area, also known as instances, but all their n-ary relations, pairs, triples, quadruples of everything in your universe. So most often this is infinitely large, right? But we don't really care about that because we will have a meta model, a language that can give us a nice tool to abstract away from the infinite number of things that we want to speak about. So on the top, we have M2, the meta model, which is the language. It includes the kinds of modeling elements that you can use to describe your world. And in the kernel core, there are actually 3 types or 3 kinds of modeling elements: type, classifier, and feature, as you can see here. Type is the most generic. Everything is a type. And you can split this into classifiers, which classify single things, and features, which classify relationships. So this is the first branching. And then you have M1, where the interesting things happen. This is what we want to build. where we define the domain concepts. So for example, we have a vehicle and a wheel, which are classifiers. We have the roles on feature. Obviously, we want to say that some of the things in our world are cars. Let's see. So these are instances of language elements. And the interpretation will map M1 concepts into M0 instances. For example, now we can say that these are all vehicles, these are all wheels. We don't say what these are. And the roles on feature are pairs, which we define this way. Okay, and there are other triples, quadruples, other pairs maybe, which are not classified by these things. So interpretation is about labeling things. Again, this is not very far from first order logic, right? We interpret our symbols. And then we will say that the set of labeled things for each concept is called the extent. This will give the semantics to that concept. So how do we know that a vehicle is a vehicle? We know because we identified the set of things that we think are vehicles. Again, a nice connection to AI. This is what we would like to have neural networks decide instead of us, right? So somehow tell them that this is how we recognize a car, and then they should be able to come up with the extent, or at least tell if something inside that. Okay, and of course, you can define constraints on M1 concepts. You can, for example, say that a roles on feature establishes a relationship between a vehicle and a wheel. And then this pair would not be a roles on feature, could not be. If we put the label on that, that would violate the constraints. Okay, so first, the set gives the meaning to the concept, but we can specify how the set should look like. Again, not very far from first order logic. Okay, is this clear so far? Excellent. So the interesting things come when we add refinement, specialization. There are many kinds of specialization in the kernel modeling language, and every one of them means that the specializing types extent will be a subset of the specialized types extent. Okay, so if we have a more special category, it will include a subset of the things in the less specific category. This makes sense. Kinds of specializations. The first one is subclassification. This is a good old generalization that we know. Funnily enough, in SysML v1 and in UML, it was called generalization. In SysML v2, it is called specialization. And the reason is that in v2, we really want to be able to read an edge in the direction. So motorbike specializes vehicle. Okay, generalization was actually the other way around, even though the arrow goes from motorbike to vehicle. But when I say that a motorbike is a kind of vehicle, so it specializes vehicle, what I really mean is that its extent should be a subset of the extent of vehicle. So far, so good. You can also specialize features. For example, you can redefine a feature in another context. If we had a roles on feature in a vehicle, we can redefine this in a motorbike to add some other constraints, for example, or identify wheels, which are wheels of motorbikes, and this will also be a subset relationship. So roles on features of a motorbike will also be roles on features of a vehicle, because motorbike is a vehicle. Okay, again, subsetting relationship. You can also have subsetting between features, which is a little bit different. So here we want to say that we have the roles on feature, but now we also have the front wheel feature, which is a subset of roles on. You could actually call this wheels, and probably it would make more sense. But the front wheels are also wheels of the vehicle, right? So you can say that a subset of all the things in the extent of roles on will be in the extent of front wheel as well. And this is the notation in graphical syntax. So these are the things that you can use between features. And there is a third or fourth kind of specialization, which is called feature typing. When we say that roles on actually associates a vehicle to a wheel, what we are saying really is that vehicle features a wheel right? So the featured wheels, the things in the extent of rolls on, are also wheels. Even though some car is running on them or some vehicle is running on them, they are still wheels. Okay, so the feature that is tied by a type is a specialization of that type. Is this okay? And now you get to the funny part, which I did not put in the presentation, by the way, that the extent of things are defined in a very interesting way. So you will actually have sequences in the extent of everything. When I say that I have wheels, I will not only speak about these wheels, I will also speak about all the pairs, triples, quadruples, which end in a wheel. Those are also wheels. They are just in a context. Okay, so these are the kinds of specializations that we can use. We also have multiplicity, of course, which is the cardinality of the extent. This is where things get a little bit shaky, because I've just said that everything will be in the extent. And here there is some magic in the formalization, which refines this a little bit, not to count everything in the extent. But for classifiers, multiplicity means the number of labeled entities. So if you say vehicle has a multiplicity of 4, you're saying that this extent has to have 4 elements, not more, not less. If you say wheel can have an arbitrary number of elements in its extent, that means exactly that. You can have 1, 2, as many as you want. You can also have ranges. For example, rolls on has 0 to 4, but for features, the number of relations for each domain element is counted. So it's not all the pairs in the extent. For every car, you will count how many wheels it has. Again, this makes sense if you think about cars. Every car should have, or every vehicle should have 0 to 4 wheels, for example. It could have more. This example is not very good, but that's it. For each car, we count the number of wheels. Okay, and the last thing to know about the core semantics is that, as I said, higher level concepts are defined on the basis of lower level concepts which have a semantics grounded in first order logic. In practice, it means that when I say vehicle is a classifier, what I'm saying is that vehicle should specialize anything, because every classifier is an anything. When I say rolls on is a feature, what I'm saying is that it subsets things, because every feature is a subset of things, right? If I have a feature called wheels, those are obviously parts of all my things. Okay, so these are the most generic things. Come on again, right? So this is hard to talk about. These are the most generic concepts in your semantic library, which have the mathematical semantics. And after that, you will add your model elements and specialize these and redefine or subset or in other ways refine what was said about anything and things and other concepts in the library. And this is how you give your semantics. Okay. Any questions at this point? This was the mathematical semantics without logic, without math. I saw the schedule and I didn't really want to formalize anything in first order logic here in the afternoon. Hopefully this was understandable. Okay, let's move on. Some other stuff which will be important if you deal with kernel modeling language models is associations. Associations are in UML as well. And unfortunately, we insisted on keeping the semantics of associations from UML, which is basically this. So associations are classifiers that represent a relationship between types. Okay, so they are not features. Features are directly relating things to each other. An association is something that relates two things to each other. But it's the own type. It can be the I don't know, the rod between the two wheels or some link that exists in real life. Okay, so this is a classifier. An important characteristic of associations is n multiplicity. You can see a couple of examples here. For example, each person has a head and that head belongs to the same person, ideally, right? And this means that person and head are in a one-to-one relationship. It's basically a pairing over all the heads and all the persons. But a person may have one home, but a home might have multiple people, right? And person and pet is associated arbitrarily. So how you can read this is that if you sit here, you're the person, you look on the other side and see that, hey, I have a head and exactly one. Because everything that I have to look for is on the other side here. And this is a constraint applied to every instance of the connected type. So if I say something like this, I really mean that you cannot have a person without a head, and you cannot have a head without a person, and they should be opposites. Okay, this is a very strong constraint. Yeah, there is a note here that n multiplicity versus participant multiplicity is not the same. So participant multiplicity is basically the arity. If you have an association, and that's, again, a classifier, it is pointing to the ends. Every end will have a single participant. If I'm a binary link, I will have two participants on each end. I mean, in total, one on each end. If I'm a ternary association, I will have a third one. But the n multiplicity is not about what the association sees on the ends. It's about what the ends see across the association. And this has a very weird semantic, mathematically speaking. But if you remember that you should sit here and look on the other side, this is a very good approach to understand. Okay, so if we have associations as classifiers, the definition and usage pattern in kernel is the classifier and the feature relationship. So connectors are features tied by associations. Okay, because this was a type, and this is a feature tied by the association. And the meaning of this is that they can relate the featuring type to the association, and that gives a context. And you can specify that in this context, I want to apply the association. And I will show you an example in a second. Let's have a unicycle. Why not a bicycle? Because the example would be too long. This is quite convenient. Let's model this as a thing consisting of two things, the wheel and the fork holding the wheel. Okay, so a unicycle is actually featuring a wheel and a fork, and it also has a connector, which I will explain in a moment. So unicycle is a classifier, therefore it specializes anything. Rolls on is a feature, therefore it subsets things, and you can see its type and you can see its multiplicity. Wheel fixed is actually an association relating wheels to forks, and therefore it specializes binary link. I didn't mention this before, but every keyword will imply the specialization of a library concept. In case of associations, it's a binary link. Binary link is the prototype of every association. And you can actually say that in wheel fixed, you are connecting a wheel to a fork. And these are implicitly star arbitrary multiplicity. And you want to keep it that way, otherwise you would specify that every wheel is connected to a fork and that fork is connected to this wheel. This is probably not something you want to do. What you want to do instead is to have a connector tied by this association, which says that in this context, in a unicycle, rolls on wheels are in a one-to-one relationship with holds wheel forks. Okay, so I redefine wheel and fixed to rolls on and holds wheel, which are features here, and also redefine the multiplicity. So now I'm telling you that whatever you read in wheel fixed is true, and the participants will be from rolls on and from holds wheel, and they will be in a one-to-one relationship. What does this mean? Any implication that shows us that the original model was redundant? Can you infer anything that is not already there? So you will actually have a single fork. In every other case, this is unsatisfiable, because you need to have a one-to-one mapping between forks and wheels in unicycle. Do you see why? Okay, so the language is full of these. Actually, you can very easily write a contradicting model. I guess this is a feature because then you can find your mistake. Some of them are validated, of course, but some of them are very hard to validate because they require inferences like this. Okay, so this was your first kernel model question.
So how do people generally validate this?
There is some built-in validation in the pilot implementation. It will not spot things like that. I expect that there will be specific tools which can do this. Again, a very nice open topic where we can apply everything that we already do. Any other questions? No, they don't. This is a good point. There is actually a change which got in the language. I don't even think it got into the language yet, but the associations were redesigned quite recently, and now they include the cross-navigation features, which means that if we go back here, we can also stay here. So what you're telling here is that you associate a wheel with a fork, but the wheel does not have anything to navigate to the fork, right? So this is currently only the association. From the wheel, you don't see the fork, and from the fork, you don't see the wheel. As soon as you add a cross-navigation feature, for example, you say that I want to put something under wheel which points to the fork across the association, that is something like a directed association. And you can now do this, but it's fairly new, so I didn't put it in the presentation yet. It will be in the next version of the standard, I think. Any other question? Who feels like understanding this? Okay. Who feels that the textual notation is easy to read? Who feels that the textual notation was probably easier to write? It was actually easy. Yes. So the point is that this will probably be write-only, and then you will generate the diagram, and it's very easy then to see all the relationships. And I guess this will be a nice workflow. Again, it depends on tool support. Okay. So now we have everything from the core that is relevant for an introduction like this. How can we build on this? So as I said, the higher level concepts are basically defined as compositions of elements in the core, and they are organized into the semantic libraries of kernel. You can actually read this. This is a very nice thing if you think about that, because before this you had to open the specification, which is 500 pages, somehow find the part that you're interested in, which is scattered in at least 3 places, and read and interpret, and hopefully arrive to the same conclusion as anybody else. Now, what you do instead is open the library where you actually see the model of, for example, what a state is. A state clearly says that it has incoming transitions, outgoing transitions, it has this performance, that performance, and so on. And this is now at least a semi-formal language and not text anymore. So this philosophy is actually quite useful, and as soon as somebody starts seriously working with SysML and kernel, they stop reading the spec and go to the library instead, because that's precise.
But you could have reference that state spread across other packages, right?
Sorry?
You could have a reference that state to the concept state across other packages.
Yes,
right?
you can, yes.
I agree that you can make it compact in a package, but
yes, that's true. You can import the package and you can reference it, and that also introduces the problem that you will have some scattered stuff, yes. I actually have a student working on something like Doxygen to generate a nice navigation tool to go get across references like this. Okay, so what is in kernel? Space and time. This is very interesting. So far, everything was outside of space and time, right? This is only first order logic. Space and time are modeled in kernel. They are not part of the core semantics. They are models that we build on top of the core semantics. You also have structure, behavior, data types, expressions, and a lot more. We won't have time to go into that, but we will go into occurrences. So as soon as we start modeling time and space, we have this 4D way of thinking, which I would like you to start practicing now. We zoom out and we see reality and our lives as a single form in 4D. Okay, this is what you would get to at the end, hopefully. So an occurrence is actually a specialization of anything, just like data value. An occurrence classifies entities that exist in space and or time, while data types are not in space or time. For example, the value 5, integers, right? These are timeless. Actually, we usually assume that there is only one number 5, because they don't even have identity. So occurrences may be in spatial or temporal relationships, and this is how you define what is in your space and what is in your time. There is no coordinate system, but you have abstract concepts and you have relationships between them. There is actually a kind of topology which is built like this, but kernel tries to be as general as possible, so it does not really specify what kind of topology it is. It just maps everything to first order logic, and then you can figure out yourself. So for temporal relationships, you have happens before and happens after, which completely separates things in time. This means that they cannot happen at the same time. They cannot even overlap. You have happens just before and happens just after, which says that they actually touch in time. So this is actually similar to Allen's interval logic, if you're familiar with that. You have happens during, which means that some occurrence is inside the time frame of another one, and you have happens while, which is mutual happens during, so they are at the same time. They begin at the same time and end at the same time. And with this, you can build any kind of temporal relationship. You will not be able to specify how far apart they are, but at this point, you are not concerned. I will have one slide at the end having a note on this. So you can have spatial relationships quite similarly, but because we usually think in 3D, there is a separate domain model which introduces 3D concepts, the dimensions, relationships across dimensions, shapes, surfaces, and so on. It's very complicated, but in the kernel libraries, you only have inside of, outside of, just outside of, which is similar to happens just before and happens just after, right? So they are touching. Mates with, I don't really understand what this is. I actually read the specification many times. It says that they don't have anything in between, so they are touching everywhere. So this is probably like 2 half spaces together, because there is supposed to be no other space around them. Anyway, you can read it, probably you can figure it out and tell me later. You have inner space of and surrounded by, which is the inside and outside of things. And you can reason about relationships like this in space. And you can have a combination as well. For example, within says that something is entirely enclosed in 4D. So it happens during the time and it happens in that space. Within both is basically the identity. So I mean equality. You have the same time and the same space. And without is completely separated in space and time. Yes?
How complex is this language in terms of quantity of operators?
Quantity of
operators like these.
So these are, unfortunately, these are not operators. These are relationships. But yes, that's a good question. I'm going to count this. My estimate is quite a lot. Yes, quite a lot. So in the core and kernel, there are probably like 30, 40 or something. That's still more or less okay. But the libraries can specialize this a lot. Okay, so other than this, the kernel modeling language does not specify a space or time model. But it's, I don't know if I put this here, I didn't put this here. Actually, this is very close to super dense time. If you're familiar with super dense time, we sometimes use it in formal verification as well, but it's quite widespread in simulation. That means that you can have things at the very same moment, but they could be still ordered. So same timestamp, but there is still an ordering. This is why it's super dense. You can compress a sequence into 0 time. I believe that kernel is equivalent to that. Okay, something that comes with all these relationships and occurrences is the notion of portions, because you want to reason about decomposed parts of stuff, right? So you want to say, for example, that the front wheel is in the front. That's why it's a front wheel. This is how you model semantics, actually. So portions are actually like parts of, I shouldn't use part is something else. Portions represent some of their occupied 4D space, some of the occupied 4D space of other occurrences. And they are also occurrences, so therefore they can have relationships in space and time. And there are specialized, or there are, yeah, basically portions with names which are already there in occurrence. Occurrence defines that it has time, space slices and points. Points are the elementary 3D thing, so they have 0 extent, while time slices are sets of points. I shouldn't say this actually, because we had an argument about this, and kernel is not a point set topology, but it can include point set topology. And in the temporal aspect, we have time slices and we have snapshots. And I have an illustration for this, again, 4D, okay? Oops. This is 4D. So you have time and you have space. For the sake of showing 4D on a 2-dimensional slide, I reduced space to 1 dimension, but I gave you some perspective. Okay, so this is a car moving across time and space. By the way, we don't have general relativity. This was considered, but SysML currently does not support general relativity. Yeah, so this is a space slice of a car, right? It encompasses all the time the car occupies, but only some of the space. A snapshot is 1 point in time, but it still encompasses all the space. So it gives you a slice in 4D, a 3D projection of your car at some point in time. You can have a number of snapshots together as a time slice. Most often these will be infinitely many, but since we don't have a time model, they might be logical time, right? So you might say that 5 snapshots, 1, 2, 3, 4, 5, are 1 time slice. And the whole extent of the car in 4D is called a life. So every occurrence has a life, which is divided into time slices, which can be divided into snapshots at the very end, and the snapshot can describe it at a given time. Similarly for space. Again, this is modeled, right? So no maths here, everything is reduced to the core semantics of classification. Compared to simple non-portion features, what we can say, and this is under investigation actually, is that a feature may occupy a portion, but it is another entity. So when I'm speaking about the car, the wheel of a car, the wheel itself is another entity. It has its own life, but it occupies a portion of the space defined by the car. They can overlap. And this is similar for steps. If I have a process which is decomposed into steps, steps are separate behaviors, but they can occupy some time in the parent process. Okay? The implications of this are currently being investigated, but this is an interesting distinction. Okay, so now we have something that is related to time and, yes?
So when somebody is defining a new element for the language like this, they must also provide the translation for formal semantics and stuff like this?
No, they have to specialize something in the library which captures the information that they want to use. So for example, when I'm defining a car, I will specialize occurrence, and then I immediately have time slices, snapshots inherited from occurrence, which is in the library.
I was thinking if you were to define a new kind of occurrence.
Mm-hmm. Yeah, so there are a number of specialized occurrences in the library. You can choose from those, or you can create your own. This is what the AADL transformation guys will do. They will identify the most special element that has everything that they want and nothing that they don't, and then further specialize it to give the extra semantics. Right? But this is what you're doing when you say you have a car. A car is a subtype of occurrence. In addition to time slices and snapshots and stuff, it has wheels. And then you specify what it means to be a wheel. Did this help? Okay. So finally, we can speak about change. And this came up quite recently, actually. So when I sent the abstract to Haniel, I was expecting that I could actually give you the final answer to this. Unfortunately, we are still trying to come up with a consistent solution, but I will give you what we almost definitely have already. So one observation is that the specification speaks about features changing value. And if you think about what I said so far, features are relations between instances in M0. How can they change, right? They classify pairs. It's not a function parameterized by time because we don't even have time. Time is captured by snapshots. So how is this change, right? And the resolution is that feature values can actually be specialized on time slices or snapshots. And when you have a feature which changes value, what you really mean is that you constrain the value of the feature on this snapshot in some other way than on this snapshot. I will give an example shortly, and hopefully this will be clearer. But you actually won't relate the car to the speed. You will relate the snapshot of a car to the speed. And then you actually get a function, because snapshot captures the car at a given time. Okay, so this is an illustration. I actually should have started this when I talked about the car and its speed. So every snapshot will bind the speed to a different value. Speed is still a feature of the car, but it's inherited into snapshot. This is a point which we have to clarify. And in every snapshot, you can give a different constraint. So instances of those car snapshots will have a given speed. What is the speed of the car live? It doesn't have a speed, right? Because the car last year maybe had an average speed, but it definitely didn't have a speed. Speed applies at a given point in time. Okay, and acceleration, for example, cannot be computed on a snapshot. It requires a time slice because it's the derivative. It captures the degree of change. Okay, features. Again, I trust that I can shock you with another textual notation example. So this, again, a car with snapshots. Let's see what we have here. What we want to capture actually is that the speed of our car changes from t0, where it is 10, to t1, it still stays at 10, and then at t2, it will be 0. But nothing, we know nothing in between. So first, we put the variable feature declared under snapshots. Okay, so now car does not have a speed, car snapshots have a speed. Then we say that in the start shot, which every occurrence has, it is defined in the semantic library. Here we will redefine speed, because this is a subset of snapshots, so it inherits speed. We redefine it to be equal to 10. And we also have an end shot predefined in occurrence in the library, where we can redefine speed to be 0, and we are free to add other snapshots, which are also subsets of the snapshots collection, where we say the speed is equal to 10. What is missing here, by the way? Nobody said that T1 is not equal to T0 or T2, by the way. So these things are quite tricky. Actually, when you start working with something that has a precise formal semantics, sometimes it tells you that, you didn't really tell me that, right? It's like synthesis in a way. If you don't specify your requirements correctly, the tool will usually give you the worst solution that you can imagine. Also in kernel, if you don't say two things are disjoint, they are not necessarily disjoint. Obviously, most of the applications will assume that If you define different concepts, they will be disjoint. It's just the semantics do not require this. Okay, so if you do it like this, values in other snapshots are unconstrained. So what we know is that we looked at the speed at t0, t1, and t2, and we saw this. What is in between? Who knows? Is there anything in between? We don't even know that. If you want to specify, for example, that from t0 to t1, the speed is actually constantly 10, it cannot oscillate or anything else, what you can do is you can define a time slice, which is again a portion which subsets time slices. Again, this is described in the library. Every occurrence has time slices. This is one of those time slices in which we redefine snapshots within this time slice to have speed equal to 10. Okay, so now what we are saying is that every snapshot which falls into this time slice will have to feature speed equal to 10. And then we also say that the time slice begins and ends at snapshots, yes, this is a mistake, snapshots t0 and t1. Should be t0 and t1. Or instead, you could actually use happens before relationships or happens just before, happens just after to tell that t0 to t1 is actually in between t0 and t1. And if you use happens just after, then you will also make sure that there is no snapshot in between which can have a different value.
Start short and end short are concepts in the core?
Yes. Yes, so snapshots, start shot, end shot, and time slices are all inherited from occurrence, which is hidden here. It's an implicit specialization, but it comes there because you said that car is a classifier. If you would have said it's a type or a, yeah, I probably actually should have written class here. No, I'm not sure. It's actually classifier. But if you put type there, you don't have occurrence as your base type, and you will not be able to access time slices and stuff like this. Okay, if you actually put part definition here, you will inherit from part definition and will have a lot of things which are defined for parts. For example, exhibited states, executed actions, subparts, and so on. Okay, this was also a very good question. Okay, so we are moving towards executing stuff, finally. One thing that is still missing is how we should interpret behaviors, because so far we were slicing cars in 4D. This is nice to have a trace, but it's still not behavior in a sense that we don't have actions, we don't have assignments, and so on. So behaviors are also defined in composition. In kernel, behavior structure should be symmetrical. The only difference is the semantics that we model. So steps are non-portion features, but they may occupy some time, as we discussed. They may be in temporal relations, and they may even be conditional, because we have decisions, we have guard conditions, and so on. And there may be a variable number of steps. So you can say that, for example, payment is performed 1 to 6 times. How many? You have to infer somehow, for example, in loops. So execution in the kernel modeling language is actually equal to refining your model into a more specific model. And this is because in your universe, you will have 4D systems. So how you can imagine this is that you're designing a car, and your universe is actually all the cars with all possible histories that you can imagine. What you really want to do is classify those which should be allowed in a real-life car. And which one it is, it will depend on real-life scenarios. But you're not classifying only the car in the factory, you are classifying the whole life of the car, including every trajectory that it takes. And therefore, if you look only on the temporal perspective, a behavior model is actually a classification of traces. Okay, so now this is something that is probably closer to formal methods. So a state machine is actually a class of state sequences. An activity diagram is more or less a set of steps executed in a certain order. Okay, so how specific shall we refine? That is a good question. We can say that we should refine to a single interpretation, but this is probably not a very good strategy because there is a lot of freedom in some of the basic concepts. Something that we started to experiment with, by the way, in the execution working group, is to unroll this model, iteratively verify implicit or inferable elements. So if you can, for example, if you saw in the unicycle, we can infer that there will be only one fork, exactly one fork, because of the association. You can do the same thing with the behavior model. If you see a step that happened and there is a succession from that step, that means the next step also has to happen because it was a mandatory succession. And this unrolling in practice looks like on the slide. So for example, you have this very simple process model. Let's forget that it's SysML or not. What you would like to do is to specialize it, right? Because refinement is specialization. And when you specialize it, you have to redefine all the elements to be more special. And what you do here is say that, yes, I still have an initial step, which is a specialization of this initial step, because of all the scenarios that begin here, this one will begin in a subset of those scenarios. This can be redefinition or subsetting, depending on what we want to do. And then init is still fine. We have an init 0, which is probably a subset of inits, which are possible. And then you can do this basically traversing this model as we are all used to. You will find a merge. This merge is a subset or redefinition of this merge, probably a subset, because everything that is classified by this, everything that is classified by this is also classified by this. Okay, this was a template for things that match this more concrete unrolled behavior as well. Then you will have process 0, which is again a specialization of process in a given context. And then you will find the decision, which again, you create a specialization for that. And you decide that you will turn back. So actually, what the next stuff that you meet is again the merge. So this is another specialization of the same merge. Okay, because these are all kind of instances of the original merge in different contexts. After you will find process 1, which is another specialization of process. Once again, the decision, and now you decide you will finish. So you create the final step, and that is a specialization of the original final step. Okay, so the whole process was refined into this more elaborate process, the unrolled process, and inside that every element was redefined to capture the meaning in this context, in this unrolled context. And if you can resolve every non-deterministic choice, every constraint, for example, every multiplicity which is not a number, then you can come up with a model which is basically straightforward. It might be the case that more than one traces are still instances of this, but those are in the same equivalence class. Yes?
I don't get why the one is the refinement of the first one.
Why?
For the loop, on the first one, you can have 3 iterations of a process, but here you just have...
Yes. Yeah, so you decided that out of the arbitrary number of iterations, this one has to, which is within the original one. So this one classified iterations of 1, 2, 3, 4, 5, 6, any number, and you pick those that iterated to. And of course, there should be generalization or specializations between the arrows as well, but obviously you don't want to see that. Right? So the conclusion is that if you want to create something that simulates or verifies SysML or kernel models, in theory at least, you should be able to come up with a trace with established links to what your actual behavior specializes. I'm not sure this will be easy to do or even feasible, but this seems to be the correct solution at this point. Okay, so executing kernel, now that we arrived to all the components we have, yeah, not like this. To instantiate or execute a kernel model, we need to first unroll the behaviors. This is not in sequence, so you don't see numbers here intentionally. You unroll the behaviors and the structure to have as many non-determinism resolved as possible. In parallel, you create the snapshots and time slices, capturing the values in different features at different times, maybe in space. And then you relate these by adding temporal relationships between behaviors and snapshots and time slices, and also binding values of features consistently with the behavior that actually made you to create that snapshot or time slice. So for example, if you have an assignment, you increment a feature, that will implicitly create a new time slice in which the value of that feature is larger by 1. So you need to have 2 time slices or 2 snapshots, and the relationship between the values of x, let's say, in those snapshots are established by the definition of the assignment. This is how it all comes together. Yes, of course, you have to respect library and user constraints. I didn't really show this, but what makes this really hard and what makes me not so confident about some things is that you can have user-defined constraints. You can use the expression language to assert some stuff about your model, and those expressions can be interpreted with your model. And this basically means, I think, that you have to use some kind of solver to satisfy or to actually execute something. We are still investigating this. It would be nice to come up with solutions which do not require a solver to simulate something, because simulation should be easy. But because of these constraints, it may be possible that we need to backtrack, for example. Okay, some notes on real time, as I promised. So far, we didn't have any timestamp or coordinates or anything. Kernel actually introduces clocks to measure time, and there are some convenience functions called time off and duration off, which you can use to reason about the start time of something or the duration of something. And there are also axioms about clocks, which constrain their values based on the temporal relations. Right? So for example, if you have something that happens before something else, it means that the time of the previous one should be less than or equal to the time of the next one. Again, this is specified regardless of your clock. It can be a discrete clock, a continuous clock, a super dense clock, whatever. These axioms are supposed to be true in any case. But I think that in general, this implies a super dense time model. And there are, of course, some elements that you can use to influence timing. For example, an after trigger is a classical example. You can say after 3 seconds, I should move to another state. Obviously, that implies a relationship between the time of value of something and the time of another thing, probably the beginning of your next state and the end of your previous state. Yes, and you can also write your own constraints with the help of these functions. This is heavily work in progress. We didn't really explore how this all adds up, but this will be a critical point, probably first half of next year. Okay, so that's all for kernel. Any questions about semantics or anything that you saw? Is there anyone who feels yes?
I think that on the bottom unrolling, right? It's okay for describing executions, but if you want to reason on the behavior, I don't think
Yes.
that's the most appropriate one, because you can have an infinite number of traces there, right? So there are more appropriate notations for that transition systems, automata, maybe to describe these infinite states and traces.
I agree, but I would also like to point out that you don't have to do this completely. You may leave some loops there, yes. So I think this will be something very powerful, that on the bottom you have a completely reified and hopefully deterministic model of very few execution traces. On the top, you have your full definition, and you can refine anywhere in between. You can unroll some loops, you can say that I decompose this but not that, and so on. But yes, mapping into formal languages is, I think this cannot be avoided at some point. Okay, so in the last part of my presentation, I will speak a little bit about activities around SysML. This will only be a couple of minutes. So if you manage to get to this point, you're very much invited to contribute and think about this, because that's what we are currently thinking about, figure out what to do with all this. Sometimes it's okay to say that, hey, this is broken, we should do it some other way. Of course, it's quite late, but it's still possible to change the course of the evolution of the language. Where can you do this? How to contribute?
Just a quick question.
Yes?
How long has it been this process of creating this new version?
I think it's about 6 years. Yes, and the timeline is that the final version of the spec was submitted this March, I think, and a finalization task force was created for 1 year to address all the issues. There was actually a public review, anybody could submit issues, and we need to reply to those issues. So what we are doing right now is crunching through all the issues and trying to come up with solutions or defer them, because that is also an option, unfortunately, or there would actually be no other way. And I think yesterday the FTFs agreed that we will charter another FTF for at least half a year. So we have time until next fall. And after that, the specification will be released, the first public 2.0 version. And after that, we will keep going, because as we had SysML 1.1, 1.2, and so on, we will probably have SysML 2.1 and so on. And anything that, I don't know, we managed to convince the world that is broken, we can fix it later. Okay, so the SysML v2 submission team was disbanded with the submission. What we have instead is the systems modeling community, which is the first OMG managed community, as far as I know. And the goal of this is to keep the people together, keep the momentum. Let's do this. So it doesn't matter that we submitted the standard, we have to keep working on this. I believe I managed to convince you why, right? So there is still a lot to do. And this community has 11 working groups at this point. Tomorrow will be the first public meeting of this community, where we will actually establish the working group. And the goal is to finalize and maintain the specifications and also build community resources, tools, whatever. How to join? Unfortunately, OMG works in a very interesting way. So the specifications are free to use. But if you want to contribute to the specification, you have to pay. Which is funny, but if you think about big companies, of course, it makes sense that if you want to influence the standard, you can come and give some money and also give some work, and then it will be as you like. So universities and research institutes can join the OMG for a very moderate price. And if you join the OMG, you can immediately join the SMC as well. If you don't want to join the OMG, or you're not an academic party, you can join the SMC for a much reduced price. It's quite reasonable. And then you can attend the meetings, you can influence the standard, and so on. I would really encourage you to do this if you have, I don't know, a couple $100. It's about that magnitude, because this is really interesting. And I believe that the impact here is huge. So if we can channel our knowledge into SysML v2 and really just put all the experience and knowledge of the formal methods community, for example, behind a language which aims to be formal, this will make a change, I think. So I would like to quickly present 4 working groups that I'm affiliated with, because I think these could be interesting for you. The first one is the semantics working group. Obviously, they are working on the semantics. All these discussions that I mentioned are going inside the semantics working group, and we have a lot of open issues. The most significant are the occurrences and portions, data flows, for example. We don't have anything about interruption or termination. For example, there is no mapping of the activity final node yet, because that should cut everything off, and we don't really know how to specify that. at this point. Another working group is the execution working group, where we don't execute members, but we execute models. And this group aims to provide guidance and some kind of prototyping for simulation or execution engines. And we are writing Annex A of the kernel modeling language specification to illustrate how you can do this. It contains many elements that you saw today, and it has a key idea called atoms. Basically, we come up with singleton types to be able to reason about instances in M0. I will not go into more details. There is an example here, but let's skip this. The conformance working group is working on coming up with a test suite for future tools to see if they actually comply with the standards. So this is crucial if you think about it. Again, if you use SysML v1, you know that there are basically no two tools which are compatible with each other. So this is called vendor lock-in, and really it would be really nice to avoid this. So we want to come up with a set of test cases in these areas. I will quickly show this slide. So this is basically about verifying the tools, testing and verifying the tools. Test generation based on grammars, based on the meta model, based on constraints. So I really believe that this is, again, in the field of formal methods. And also it's a really nice feeling to come up with criteria for some tool to be able to say that they are a SysML v2 tool. Right? So we really want to make sure that this is well defined. And the fourth one is the formal methods working group. This is recently founded, so we didn't really do too many things. We had one meeting, and we will have the next one, I think, next week. This is founded by 4 tool developers: us, FBK with NuXMV, I'm sure you know about that, Imandra, which is an American, a US company, and NPS, which is a university in the United States as well. Yes?
So Imandra, I know a little bit. I mean, I know somebody who works there.
Mm-hmm.
As far as I know, they do verification for stock market.
Yes,
So
a lot of financial applications.
That domain.
So their tool is actually quite generic. There is an OCaml-based input language, and they are also mapping SysML v2 concepts into that language. So the way, basically what we are all doing here so far is translating SysML v2 or kernel concepts into formal languages, because that seems like the right way to do it. Unfortunately, the semantics is not defined like that, but we can still map into our own language and somehow verify that it is consistent with the semantics. So I believe this is a good approach. And this group is recruiting, I would say. We will have a couple of tool demos in January that will be open, so you can come and see where we are right now. And yeah, just a quick glimpse of what we are planning. Let's show this slide real quick. This is an imagined workflow of verifying SysML v2. So you come from the pilot implementation or something else. We actually have a tool called the Gamma State Chart Composition Framework, and the purpose of that tool is to convert SysML v2 representations into an intermediate language and then convert to formal languages of model checkers. And currently we support our own model checker called Theta, NuXMV, Upal, and Spin, but it's not very hard to integrate new model checkers. And what is really nice in v2 is that now you can actually describe what you want to prove in the language. I already mentioned this very quickly, but you can have a verification definition which says that on this system you should prove this requirement. And you can even see that I have a homemade library for temporal operators, which you can define on top of the core semantics. And then you can also have other kinds of verification definitions, for example, for test generation. And you don't need to have complicated UIs anymore or right-click menus or whatever. You just have the model itself describes what should be verified, and you just do the job. Okay, so this This is the idea here, and it would be really nice to expand the set of tools here. It would be really nice to refine the transformation chain and to come up with a consistent semantics together. So there is a lot of things to do here. If you're interested, feel free to join. I plan to have meetings which are not only SMC, so others can contribute who don't have memberships. Okay, and at this point, yeah, there is a demo available, but I guess something happened to, yes. And at this point, I have a shortcut here. Let's jump to the end, please. Okay, it doesn't really work. Yeah, because it's not that computer, okay. Makes sense, right? Yes. Conclusion. So for some reason, I don't know, is this Google Meet or Zoom? It didn't really want to transfer my clicks, right? Okay. So conclusion. As a summary, I hope you have seen that MBSE has a lot of use cases for formal methods. And in SysML v2 and kernel, semantics are quite exotic, but they are not very far from what we are used to, especially if you are dealing with solvers and ontologies. It would be nice to somehow learn this and map it into known theories and algorithms, because then we could reuse the past 40 years of research in formal methods. I would think that is worth trying at least, and I'm trying to convince everybody on the other side that they should pay attention to what we do and maybe listen to us. That would also help. And there is this systems modeling community which now offers a very, very nice opportunity to work together, to contribute and to share experience. So I would like to encourage you to join the SMC. This is the time for recruitment, and just bring your tool, bring your expertise, and we should try to make this work somehow. Thank you very much for your attention.
Further questions?
I guess it's quite late and you had a lot of questions in the meantime, so thanks again and see you tomorrow.
So we have a pipeline from agree to our model checker setting. It goes agree to register to setting.
Right. Whoever wants to join us tomorrow for the dinner, just send me a message, okay? We have to make a list. For those who are not in the list we had before and want to join, is 160 per person, okay? Just in case. But if the list is not full, we may make some spot tomorrow, someday.
How do we know who is in the list?
Well,
How do we know if, how would I know if I am in the list?
all guys are in, you are in this. I mean, outside.
So
Okay.
non-participants, right?
Yeah, non-participants. Yeah, yes. Yes.
Okay.
So perhaps tomorrow we'll pick up some lucky guys to go. Okay, but just in case, tell me if you'd like, send me a message. Okay.
Yeah, so you were saying that there's an effort to port ADL with the agree language to SysML. So we should probably join that effort so that our pipeline from agree to our model checker can be lifted from SysML to our model checker just to add to the list of model checkers and then we don't keep breaking.
That would actually be a separate talk as well, which is also happening. Because it's nice to have a single transformation because everybody can contribute and you can everyone semantics, but it's also a single point of failure to get something right there. Which I think this is great. But if you have at least two or rather three implementations, it would be nice to check if all of them say the same.
But yeah, this was basically step 2.
There are other model checkers that may be interesting to plug into the ecosystem, like PDKind, JKind, Iowa stuff.
Yes, I actually have a long list of people who I should contact, but it would be nice to not do this alone.
Oh yeah.
Oi. Escrevi ontem pra hoje. Consigo fazer o credenciamento? Tem que ver com as meninas aí fora, Débora. Ela tá aí fora ainda?